students, early research enthusiasts in the course. This course on climate change and urbanization is being conducted under Global Initiative of Academic Network, GIAN scheme, Hyderabad and organized by MAT. The program GIAN aims at encouraging scientists and entrepreneurs internationally to engage with institutes in India. The effort, funded by Ministry of Education, Government of India, intends to elevate India's scientific and technological excellence and exposure to international level through interaction between students and faculty globally. The course will engage the participants for 5 days in lectures and tutorials conducted by international faculty expert Professor Rafiq Hamdi from Royal Meteorological Institute, Belgium, and host faculty expert Dr. Surbhi Mehrotra. The curriculum is coordinated by Dr. Mehrotra from Department of Architecture and Planning and Professor Jyoti Sarup from the Department of Civil Engineering. Professor Subimal Ghosh, Dr. Divya Sharma and Saransh Vajpayee has been invited as Indian experts to provide insights into the current research and industrial developments in the domain of climate change and its impact on our cities. I would now request the dignitaries, Professor Rafiq Hamdi, Professor Karmesh Kumar Shukla, Dr. Satish Pal Singh Rajput, Professor Alka Bharat, Professor Mukul Kulshrestha and Dr. Nakul Dhagat to please come up on the dais. I would request Dr. P.T. Omkar, Professor Jyoti Sarup and Dr. Surbhi Mehrotra to join the dignitaries for Saraswati Pushpanjali, offering flowers to the idol of Goddess Saraswati, revered as the deity of knowledge, education, learning and arts, and Deep Prajwalan. This would be followed by Jal Arpan. The plant being used for Jal Arpan has air purifying quality and medicinal benefits. A living relationship in a physical or in a social body depends upon sympathetic collaboration and helpfulness between the various individual organs or members. When a perfect balance of interchange begins to operate, a consciousness of unity develops that is no longer easy to obstruct. The resulting health or wealth are both secondary to the sense of unity, which is the ultimate end and aim, and a creation in its own. This was stated by Rabindranath Tagore. Water is one of the life-rendering elements of urban areas. Climate change has profoundly affected water resources, altering its availability, quality, and reliability. These changes have far-reaching consequences for ecosystem, agriculture, human health, and overall socio-economic stability. Water is one of the factors that threatens transboundary peace. With this grazing note, we will continue with Jal Arpan. As said by Dr. Pratibha Dwivedi, पानी की महिमा बड़ी रहीमन दिए बताए, मानव तो मूर्ख बड़ा सीख सभी बिसराए. As the water flows through nature and helps it blossom, I wish that it inspires us to nurture our commitment to knowledge and progress. With this, I would invite Professor Karunesh Kumar Shukla, Director Management, to felicitate Professor Rafiq Hamdi, Professor in the Department of Meteorological and Climatological Research at Royal Meteorological Institute of Belgium. I would request Professor Mukul Kulshesha, Head of the Department Civil Engineering, MANET, to felicitate Professor Karunesh Kumar Shukla, Director, MANET. I would request Dr. Nakul Dhagat, Head of the Department at Architecture and Planning, MANET, to felicitate Dr. S.P.S. Rajput, Dean Institutional Development and International Relations, MANET. I would request Professor Jyoti Sarup, Professor at the Department of Civil Engineering, MANET, to felicitate Professor Alka Bharat, Dean Faculty Welfare, MANET. I would request Dr. Preeti Omkar, Local Coordinator of GIAN and Associate Professor at Department of Architecture and Planning, MANET, to felicitate Professor Mukul Kulshesha, Head of the Department at Civil Engineering, MANET. I would request Professor Jyoti Sarup, Professor at the Department of Civil Engineering, MANET, to felicitate Dr. Nakul Dhagat, Head of the Department of Architecture and Planning, MANET. I would now request Dr. Survi Mehrotra, Host Faculty of the course and Assistant Professor in the Department of Architecture and Planning, to officially commence the proceedings with the welcome address.
Suprabhat and namaskar to all the dignitaries on the dais. We welcome you all for the inaugural function of this GIAN course on climate change and urbanization. Global Initiative of Academic Network, GIAN, facilitated this opportunity to MANET Bhopal to design and conduct this course on climate change and urbanization with the help of international experts, renowned researchers for the Indian students and professions. Climate change and urbanization is a comprehensive course that examines the complex interplay between the urban development and the impact of climate change on, again, urban areas. I thank Professor Hamdi from Royal Meteorological Institute for agreeing to provide insights on interrelationship between urban areas and climate change through climate change modeling processes. I will be covering upon the planning and design of climate change impacts on urban settings and how should we plan a climate sensitive urban areas. This course is designed with interdisciplinary approach for creating an holistic understanding of the process of urbanization with the help of lectures, tutorials and practicals on the ground. We will be doing observations on the ground in the Institute of Managed Bhopal itself. The lectures will be webcast live on YouTube for the global access. By participating in this course, students will gain the invaluable insights and international perspective in the domain of urban climate. Now I would like to invite the patron of the course, the head of the department, Architecture and Planning, to address the students and encourage to join this course. Professor Nakul Dhagat sir.
Namaskar. Dr. Hamdi, welcome to MANET. Director sir, Rajput sir, Mukul sir, Alka ma'am, all the faculty here and the participants. It's a pleasure for me that our department, in collaboration with the Department of Civil Engineering at MANET, is hosting this course. As a layman, I can understand that I have been feeling the changes because of the climate change, and I'm sure the deliberations and the learning during this course will definitely benefit the participants, their organizations and the society as a whole. I welcome everybody again. My best wishes to the coordinators so that this course becomes really good success and a platform for many more such courses. Thank you for joining. Thank you so much.
I would now invite the patron of the course and head of the department at Civil Engineering MANET, Professor Mukul Kushesha, to address the gathering.
Respectable dignitaries on the dais, off the dais, my friends, students, dear students. Most welcome outside participants, also most welcome here. Please give time, since you are here, please give time, visit our labs, have interaction with our faculty. Probably we can have some collaborations, so please give some time outside of your course. And please, the coordinators also may please give us the program so that my faculty and my students, if they like and if you have vacant seats, they can sit down here and gain something because the expert has come from outside. So please give us that program, so hopefully it will be a gain for all of us. This topic is, it could not have come, this is the mother of all problems, climate change. I would not like to go into, this is very dear to me because it's my area also, a little bit. I know a little bit of that ocean, but this is not the time for that. But it is the mother of all problems, that the ultimate constraint which humanity is facing. This is the time to save ourselves. This is really, really most topical at this time. Most welcome once again. Thank you so much.
I would now invite the patron of the course and Dean Institutional Development and International Relations, Dr. Satish Pal Singh Rajput, MANET, to address the participants.
Namaskar. The chief guest of today's function, Professor Hamdi from Belgium, our director, Professor Shukla, head of the department, Civil Engineering, Professor Kulsresht, Architecture and Planning Professor Nakul Dagat, Dean Dr. Alka Bharat, and other dignitaries, students, participants, and friends. Yesterday, the coordinators of this workshop or the host faculty, Surabhi told me you have to speak only the 2 words because time is less. So instead of speaking 2 words, I will give you only 2 aspects of this particular program. This is the GIAN program, and our institution since long is aware or doing a lot of work over the climate change. As I remember in the year of 2010 and 11, when Japanese professor has got the Nobel Prize, I think he's from Japan or some other countries, one of our senior professor, Professor Manmohan Kapse, has contributed a lot to achieve that Nobel Prize over the climate change. So we are thinking, what are the effects of this climate change? What are the reasons of this climate change since 2010 and 11? This is the one thing which gives the proud to the Department of Architecture in particular and MANIT in general. The second thing is that when this new education policy came into existence in 2020, 3 years or 4 years back, from 2015, a lot of seminars, workshops, conferences were going on for the discussion over this new education policy. Once I asked after a program to Professor Kasturi Rangan, what is the necessity to implement this new education policy? He told me, or these are the lines of that 62-page document of the new education policy, 3 or 4 initial lines, top lines. Everything is changing. Earlier, when the education policy were there, we were 40 crores. Now we are having 140 crores. Eating habits are changing. Human styles are changing. Clothing habits are changing. So let's have a change in the education policy. And even the climate is also changing. We have to think. As far as the urbanization is concerned, rural background is concerned, in order to implement the effects and our preparation and planning for the change of the climate. In last 1 year, MANIT has conducted 46 faculty development programs, workshops over such type of important topics, 13 international conferences and more than 15 memorandum of understanding from the different institutes. I congratulate to the coordinators for this workshop, and once again I welcome Professor Hamdi from Belgium on behalf of the MANIT Bhopal. Thank you.
I would now invite the Chief Patron of the course and Director MANIT, Professor Karunesh Kumar Shukla, to address the course participant and audience.
Namaskar. Professor Hamdi, the main speaker and chief guest of the inaugural function of the GIAN course on climate change and urbanization. Professor SPS Rajput, Dean in ID and IR. Professor Alka Bharat, Dr. Nakul Dagat, Professor Mukul Kulshrestha, coordinators of the workshop, Dr. Surabhi and Dr. Jyoti Sarup, my faculty colleagues, participants, dear students, and those who have joined through online mode. I welcome you all to the inaugural function on the GIAN course on climate change and urbanization, and also I welcome to the MANIT campus. As Professor Mukul and Professor Rajput has said that this is one of the important topics which we have been discussing as a human being. And the topic, I really appreciate the coordinators for choosing this one, the impact of urbanization on climate change, and I was going through the themes. So starting from the planning to the different aspects, how it is affecting the climate. I hope that the experts, including Professor Hamdi and the other in-house and outside experts, will deliver and discuss on these aspects. And this is the one thing which we as a human being have to think about. We are talking about that what will happen after 40 years or 50 years. You might be reading in the newspapers that the cities near the coastal areas, as the temperature is going on, there will be rise in the sea level and they are going to submerged in water. Something is also said about the Mauritius and other countries. So this is the role of the planners, the engineers and technocrats to think about how to mitigate the effect of urbanization on the climate. And our country is also committed to go for the carbon neutral in next few decades. So whatever the development is it is going to take place, it's directly affecting the climate. And if I can put it in a mathematical sense, that urbanization is directly proportional to the adverse effect on the climate change. So we have to have a striking balance in the urbanization and the impact on the climate change. In our country, and in fact in our religion, if you go to the Rig Veda has dealt with the impact of climate on the human being. That's how we have been following the yajna from the ancient times, that is to purify the Mother Nature. Goswami Tulsidas has also said about the existence of the human being or our the body, that Chitijal Pavaka Gagan Samira Pancha Rachiteya Adam Sarira. That our body comprised of 5 elements. And if you go to the Ayurveda, they talk of these elements: Akash Tattva, Vayu Tattva, Jal Tattva, Agni Tattva. And based on these, they try to cure the disease. So in fact, our philosophy is based on the environment itself. Even our own existence is based on these 5 elements, be the water, be the air, be the sky, be the sun, all those things. These are the 5 elements which is comprised of our body. If you go to Bhagavad Gita, the chapter 2, if you take the verse from 4 to 10, 2.4 to 2.10, Lord Krishna has narrated to Arjuna about the importance of the climate. So, we have been saying from the ancient times the importance of the climate and its impact. Unfortunately, with the rapid advancement in urbanization, somehow we lost this. Now, this is the right time for the engineers, technocrats, designers and planners to think about it, so that the impact of development is mitigated on the climate change, and we can make this planet livable for the future generations. So once again, I congratulate Department of Architecture and Planning, Department of Civil Engineering, the coordinators, Dr. Surbhi, Dr. Jyoti Sarup, head of the departments, Professor Mukul, Professor Nakul, for organizing this conference. And I welcome Professor Hamidi, who have taken all the pains coming from Belgium to man it. We welcome you and hope that during these 5 days we'll have a meaningful dialogue and discussions, and your stay would be very pleasant. Please enjoy the stay at Bhopal. Take a tour to the near about the Bhopal. And I request the faculty colleagues and the research scholars, students to establish a dialogue with the Professor Hamidi and other speakers. Thank you. Take care. Jai Hind.
I would now invite the chief guest and foreign expert, professor in the Department of Meteorological and Climatological Research at Royal Meteorological Institute of Belgium, Professor Rafiq Hamdi, to address the participants.
Good morning, everyone. First, I would like to thank you very much for this. I am honored to be here. So, faculty, department, and dear professor and esteemed student. Just to say, I'm very honored to be here. I need to thank GIAN program to be able to give me the funding to be here. For sure, Manit for hosting this. So I am really deeply honored to be here. And I think, yeah, a lot has been said already on the climate change and urbanization. We will have the opportunity to discuss this during this week. So I will be brief here. So I don't need to talk a lot after all this exceptional introduction from the dignitaries. So we will have time to discuss together on climate change, urbanization, throughout the lecture and also the tutorial that we will do together, the exercise. So yeah, thank you very much and see you soon.
I would now invite Professor Jyoti Saru, Professor of the Department of Civil Engineering, to deliver the vote of thanks.
Respected today's chief guest, Director Sir, Dean Sir and Madam, Head of the Departments, Dr. Mukul Kulshresh Sir, Dr. Nakul Dagat, and our Institute Coordinator, GIAN, Dr. Preeti Omkar, distinguished faculty members, participants and students. It is my privilege to deliver the vote of thanks as we embark on this journey towards the course on climate change and urbanization. Through the sessions, we aspire to lay the foundation for an incredible path of learning and collaboration. This would have not been possible without the contributions of several key individuals who have guided and collaborated with us to take the necessary steps. First and foremost, I would like to sincerely thank the Ministry of Education for providing the platform of GIAN, Global Initiative of Academic Networks, under which this course has been made possible, fostering a unique space for academic excellence and knowledge exchange. I also extend a heartfelt gratitude to the Indian Institute of Technology, Hyderabad, as a GIAN coordinator. A special thank goes to our esteemed instructor and speaker, Professor Rafiq Hamdi, whose gracious acceptance of our invitation to conduct this lecture series is deeply valued. We are grateful for this commitment and dedication, traveling all the way from Belgium to India to share his invaluable expertise with us. We are thankful to Professor Subimal Ghosh, Dr. Divya Sharma, Mr. Saransh Bajpayee, Dr. Vikas Punia for their willingness to dedicate their valuable time to this course and lecture series. Your commitment to sharing your expertise and insights is truly appreciated, and we are confident that your contributions will greatly enrich this learning experience for all the participants. We are extremely grateful to our Chief Patron and Director Sir, Professor Karunesh Kumar Shukla ji, to support us and keep us motivated through our journey. This organizational endeavor would not have succeeded without the collaboration and constant guidance of our Dean ID Sir, Dr. SPS Rajput, Professor Mukul Kulshresh, Dr. Nakul Dhagan and Dr. Preeti Omkar. I would also like to acknowledge our organizers and support staff who work and who contribute further to ensure the seamless execution of this course. And also I thank to the distinguished faculty members who are present here. So thank you all for your enthusiasm as we begin this remarkable journey through the upcoming course and lecture series. So wishing everyone a fruitful and enriching experience ahead. I again thank all, and we would now break for a high tea, and we will be gathering again and reassembling again for a keynote address by Dr. Subhimal Ghosh. Thank you, and you all are invited for the high tea.
has been a leading voice in his field and has received numerous prestigious awards, including the Alexander von Humboldt Medal 2024 and the Shanti Swarup Bhatnagar Prize 2019. He is a fellow of the National Indian Academy of Engineers, the National Academy of Sciences, India, and the American Geophysical Union. Recognized as one of the 75 scientists under 50 who shaped today's India, he has authored over 200 book chapters and research papers. Sir has been instrumental in climate policy and research in India. He led the draft writing committee for India's Climate Research Agenda 2030, which was published by the Department of Science and Technology in 2023. He also served as a lead author for the IPCC's 6th Assessment Report and contributed to Kolkata's Climate Change Action Plan. His innovative work in hydrology and climate science has earned him several patents and prestigious fellowships, including the Swarna Jayanti Fellowship and the BOYSCASC Fellowship for the Advanced Research in the United States. Sir is an inspiring teacher and a mentor and has been honored with the Department Excellence in Teaching Award at the IIT Indian Institute of Technology, Bombay. He also serves as an editor for leading journals like Cambridge Water and Frontiers in Water. His work has bridged the gap between academic research and real-world applications, helping to address pressing environmental challenges. Today, we feel deeply honored to have us a visionary leader whose career exemplifies dedication, innovation, and significant impact. His contributions to climate science and sustainable water management have left an inedible mark, influencing policies and practices at both national and global levels. Sir, your work inspires us all, and it is a privilege to have you with us. With great respect, I am delighted to introduce you and warmly invite you to deliver your presentation. So we don't even we are still not able.
Can you hear me?
Yes, sir, we are able to hear you.
Should I start? Should I start?
Yes, sir.
Okay. Thank you for the kind introduction. Yes, so today I will be talking about urban climate extremes, the changing pattern, and early warning. So I will give you some ideas of what exactly we are doing. So when it comes to extremes, as we all know, and IPCC working group 1, working group 2 have been telling us that human-induced climate change is already happening. It's not a futuristic thing. It's actually happening now, and it's affecting different parts of globe. And there are evidences of observations like increase in heat waves, heavy precipitation, droughts, tropical cyclone, everything. So of course their attribution to human influence has kept them still verified. So now the thing is something like this. We know that climate change is affecting us. Now we are looking for some solution. So what do you support? And for a country like India, where adaptation we need to improve, we need to improve our adaptive capacity. We are lacking in terms of adaptive capacity. We means most of the population of our country. So then, for that case, we have to improve the adaptation. And any adaptation strategy which is for climate change, it should be founded based on the foundation of climate science. Otherwise, this adaptation can be maladaptation. So what we need to do is that we need to think of adaptation, we need to think of climate services, but that should be based on solid climate science. So with this, I will just quickly go through figure which we generate as a part of IPCC Assessment Report 6 Working Group 1, where we tried to understand that how human influence has actually impacted heavy precipitation. So in the IPCC Assessment Report 6 chapter, where I was one of the real planners responsible for the part heavy precipitation. So if you have time, please go through IPCC. Many things. There are few things which are very important in this report. One of them says that urbanization plays a role. So the first time IPCC has very clearly said that there is confidence that urbanization lead to increase in extreme precipitation, which is very important. The second thing also IPCC said is that the second thing IPCC Air 7 is coming, well, one of the major thing is that city and climate change. So it shows that cities are mostly affected because of climate change, because high population, high infrastructure, and so on. Now, if you look into the precipitation and human influence, so we are sure that heavy precipitation has increased. So this is represent the globe in terms of this kind of hexagons, and the South Asian region where India is located, and you can see we say that there has been increase in extreme precipitation, but there is confidence that it can be attributed to human contribution. This is because of limited agreement. Why limited agreement is coming? Because first thing is that models are not very good for precipitation, so there is a huge uncertainty. The second part is that there are a lot of local changes which also affects the precipitation, extreme precipitation specifically, and quantifying them is one of the major challenges. And urbanization is one such thing. So now I will go back to one of the very famous paper which was published in 2006 by Professor B.N. Goswami, which first said that extreme precipitation in India is increasing, and what they have done is that they have picked up a box over the central India, and when they plotted the trend, what they have found is a very extreme rainfall, that means where the rainfall amount is greater than 150 mm per day, that two occurrences have increased, and also greater than 100 mm has increased, whereas medium rainfall, which is 5 to 100, they have actually reduced. So, and they said that essentially the extreme precipitation have increased. So after that, what we started, we wanted to see that okay, extreme precipitation have increased, that is fine, but let us try to understand that if the spatial variations of extreme precipitation has increased or not. And what we have found is that if you are going at a local scale, you will get a mixed kind of changes. Somewhere it's increasing, somewhere it's decreasing. So increasing points are higher in terms of numbers, and there is huge spatial variability. So one of the things we started hypothesizing is that the increase in extreme precipitation. So if you look at the spatial variation of trends, that has increased quite significantly. You can see that from 1950 the spatial variation of trends have increased quite significantly. What does it mean? It means that the changing pattern of one region is becoming very different from the changing pattern of other region, and that shows that if it is because of just global change, then all of them will have very similar kind of trend. But when local factors starts playing into it, then you will get these variations, this spatial variation, and this is increasing. That clearly shows that probably our spatial, probably some of the local changes are actually playing a major role. So we published this one in Nature Climate Change long back in 2012, and then one of our student started working on something else. So what he started to do is that he tried to find out before 1950 the changes and after 1950 the changes. And this is some sort of a distribution. Before 1950 you can see that 46% of the stations are showing increasing trend in India, 30% decreasing, and 21% no trend. And after 1950, 46 has become 47, 33 has become 30, 21, 20, not much of change. But grid-wise, there has been a lot of dissimilarity. You can see that 75% of the grids having no similarity. That means increasing has changed to decreasing, or decreasing has changed to increasing, and so on and so forth. So there has been a reversal of trend at many occasions after 1950. So you can see before 1950 increasing, among before 1950 increasing, only 45% are continuing to be increasing. Similarly, before 1950 decreasing, only 49% are continuing to be decreasing, and notice something like this. So it really shows that there has been a lot of change in terms of trends. Then what we try to do, we try to use on the change point analysis, where we are trying to understand where the trend has changed, with which year. And try to understand if it is if the change point year is in between 1900 to 1925, or 1925 to 1950, or 1950 to 1975, or in between 1975 to 2000. We are trying to understand where it is happening. And what we have found is very interesting. We found that the regions with high population, and when there are some built-up region, if you consider only those lists, what we are finding is that 51% of the change points, that means 51% of the grids are having change points after 1975. Now 1975 is something after which we are seeing extensive urbanization in this country, and you can see that highly populated regions or urban regions are showing, most of the grids are showing change point after 1975. But if you are considering non-urban regions, you can see it's well mixed. So that clearly shows that it is one of the GIAN paper where that started saying that look, urbanization is actually playing a major role. Most of the urbanized regions are showing change point after urbanization. So at that, then we have come to very specific questions. Let us look at all India and find out urban regions are getting any specific kind of changes or not. So this was done again long back 2015 by one of our students. What she is trying to do, she is trying to pick up some of the urban regions and consider the 100-kilometer radius and outside region, and she is trying to understand if there is a change in the trends. And what she has found is something interesting. So let us pick up this plot. This is all India, and this dotted line shows the percent of increase and percentage of urban regions. Now if you consider it, this increasing trend points, among these increasing trend points, how many are urbanized regions? Among decreasing trend points, how many are urbanized regions? And when she looked at it, what she found is that if you consider the southern zone and the western zone, these are the regions where you can see that post 1950 you can see very strong urban signature, because this one is crossing the dotted line. That is, the increasing trend urban fraction is more than the normal urban fraction. That clearly shows that urbanization is playing major role. To make it more clear, what we did is that we divided the time period into two parts, 1951 to 1978 and 1979 to 2007. And when we did this, now look at it very carefully. Now you can see that increasing trend points are actually crossing this dotted line because of urban. That shows they are because of urban signature. And very prominent in this report is 1979 to 2007. There is a near past graph. This is the long past and this is the near past. In the near past, you can see that every region, the urban signature is becoming very important, and that clearly shows that urbanization is playing a major role in terms of increasing the extreme precipitation. Now, of course, the question now comes is that how does urbanization affect extreme precipitation? How does it result into increase in extreme precipitation? So there are specifically 4 ways by which you can think of urbanization may result into increase in extreme precipitation. The first one is that urban heating. So we all know that urban regions have higher temperature, and when you have higher temperature, the air has more moisture holding capacity. With part degree increase in the temperature, the moisture holding capacity increases by 7%, and this is by the Clausius-Clapeyron theory. So Clausius-Clapeyron thermodynamic theory says that Now urban regions will have more moisture. So when it comes in terms of extreme precipitation, this is getting reflected. We all know that Glossier platinum is only reflected in terms of extreme precipitation. So you will expect that urban regions will have more extreme precipitation. The second thing is that urban heat island effect. That means urban regions are having higher temperature compared to the nearby non-urban region, and because of which there will be a differential heating, and there is a differential heating that results into more circulation towards urban regions, that results into more rainfall. Reasons, urban regions generate more pollutants. So essentially pollution is more, so the aerosols are more, and aerosols are cloud condensation nuclei. So they help in formation of cloud, and when they help in formation of cloud, that results into more extreme precipitation. And the fourth one is because of urban structures. So how does it happen? So for example, let's say in urban regions there are a lot of built-up regions, high-rise buildings, slums, low-rise buildings, and so on and so forth, roads. So what happens if you assume that there is nothing in an urban region, there is a huge wind that is coming. They have the full cross-section over the urban regions to flow. But when the structures, the wind flow gets restricted, and so the cross-section area gets restricted, so the velocity increases, that results into more eddy generation because there are building corners and everything. And when there is more eddy formation, more instability, and in more instability means more cloud formation and more rain. So urban structures also result into increase in extreme precipitation at certain pockets in the urban region. So we want to do some kind of statistical hypothesis testing to try to understand that if urban regions urbanization really result into extreme precipitation. So what we did, we have picked up two regions. One Mumbai, of course, highly urbanized region, and the second one is Alibag, which is exactly at a very similar geographical region, very close to Mumbai, but it is a town sort of thing, so it's not an urban region. So we wanted to see that if we consider Mumbai and Alibag, do they show similar kind of extreme precipitation change or different? If they are different, then that shows that urbanization is playing a role in Mumbai. So what we did, we have the data for both Mumbai and Alibag from 1969 to 2008. So what we consider, we divided the data into two parts. One is 1969 to 1988, and the second one is 1989 to 2008. Of course, 1989 to 2008 is considered to be more urbanized compared to the first half. Now what we did, we performed a quantization. I'll tell you what exactly we have done. So if you look at Mumbai and Alibag here, and these are the large scale circulation pattern. So this large scale circulation pattern, some results into wind circulation, and that results into extreme precipitation over here. Now, if there is no change, then this large scale circulation pattern will result into some kind of rainfall. So that if you have observed rainfall and large scale circulation pattern as a relationship, if they are same for Mumbai and Alibag, that means there is no impact on urbanization. So that's what we exactly tried to do. What we did here is that we took the reanalysis. Of course, we did some dimensionality reduction in principal component, did some clustering and so on. And finally, what we tried to do, we tried to understand if the circulation pattern that results into extreme precipitation under that class, if the relationship between rainfall and circulation pattern has been changed or not. And this is what we tried to do. So when we did that, we have found something interesting. First, what we have found is that there is one specific circulation pattern that results into precipitation over this Mumbai and Alibag region. This is cluster 1. Now, if you look at 1969 to 1988 and 1969 to, sorry, this is the second part. So if you consider them, if we find that there is a decrease, actually there is a decrease in cluster 1. So that means the large scale circulation pattern extreme precipitation has actually slightly reduced. Then what exactly is happening? Then when we checked in Mumbai and Alibag, we did some quantization where we are trying to understand, given a circulation pattern, what are the changes you are expecting in terms of extreme precipitation. This is what we are trying to find out. And when we are trying to find out what we are finding is that, let's say these are different quantities and these are the values for cluster 1. And what we are finding is, the first one is for 1969 to 1988 and second red one is 1989 to 2008. This is for Mumbai and this is for Alibag. We can ignore cluster 2, 3, 4 because they do not result into very high rainfall. So you can clearly see that in the recent half year for Mumbai, there has been a sudden increase in extreme precipitation. And if you look at Alibag, it's not happening. So that clearly shows that even the circulation pattern that results into extreme precipitation, because of urbanization, the more generation of extreme precipitation is happening over Mumbai compared to Alibag. Alibag it has reduced because circulation pattern has reduced. But in Mumbai, there has been a significant increase and that association has also changed because of urbanization. So that clearly shows that urbanization is resulting into extreme precipitation in Mumbai. Now, so one of the major things when you're talking about extreme precipitation in Mumbai, this urbanization also affects the spatial variability within the city, and this is quite well known. So if you remember, in 2005 there was an extreme precipitation in Mumbai. Santa Cruz on the station receives 900 mm of rain in just 24 hours, and 20 km away there is another station which receives only 80 mm of rain. 83 mm of rain. So that shows this sort of urbanization. And this urbanization is well known to the Mumbaikars who live in Mumbai. But what we wanted to understand is that what exactly is the reason behind such a huge spatial variability within the city. So what we did, we have done a very high resolution physics-based modeling with the help of weather research and forecasting model, which is essentially a dynamic downscaling model. So we consider the Indian region like this, and we have run the model at 3 km resolution, so high resolution. And what we tried, and this in Mumbai also we have around 6 weather stations which are available set up by BMC to understand the spatial variability. Now we have considered 3 cases of simulations. One is we have not considered any urban canopy model. We have considered urban radiation effect. That's it. As second one, we have considered a single layer urban canopy model. Urban layers are represented by just the same height of building. So the wind profile gets changed because of this. The third one, we are considering multiple height buildings and so on, which is high resolution model. This is multi-layer urban canopy where these eddy formations are happening. So our purpose is to understand these eddy formations, will they result into more extreme precipitation or not. So this is something what we did. So this is the observed rainfall on one of the extreme rainfall. If you do no urban canopy, we are unable to present. If you are doing singular urban canopy, but still not. But when you have multi-layer urban canopy, you can see that there is some matching which is happening. So this is the mean precipitation. This is no urban canopy, and single-layer urban canopy they are not matching. But when you are doing multi-layer urban canopy, it's matching. Except for this, for all other days, you can see that multi-layer urban canopy is quite well representing the Mumbai's rainfall. Now the second important part is the spatial variability. So we also plotted the spatial variability of Mumbai rainfall. So this is the also spatial variability. As I told, that a huge spatial variance across the stations. But if you do a no urban canopy or urban canopy, they cannot represent. But if you do multi-layer urban canopy, then you can reaching actually the spatial variability which is there in observed. So let us look at this. What exactly is happening? Let's focus on this figure, specifically this figure. Zoom in and focus on this figure. So you can look at it, you can find that this is essentially the observation. The blue line is the observation of the spatial variability. That means how different one station with respect to another station. Now if you don't use any urban canopy model, it goes like this. If you use single layer urban canopy model, it goes like this. But when you are doing with multi-layer urban canopy model, that means building structures and everything, then you can see it is producing high spatial variability, and this is happening simply because we are having these eddies which are forming, and that results into increase in spatial variability. So this is what I wanted to say is that if you look at Mumbai, the extreme rainfall pattern, you can see this is the region which is reaching low rainfall, this is the region which is having high rainfall and so on. This is one of the days, this is the average annual maximum rainfall. Now when you are doing it with urban canopy, so this is what I wanted to say, maybe I zoom in again and I try to show this part. So if there is no urban regions, you will get extreme rainfall like this. But when there are urban urban regions, as I said, that there are few pockets which results into extremely high rainfall, and that results into a high tail, more spread distribution of rain, and that makes it really challenging to model the urban extreme precipitation. And what we have found is that Shubhanta Paul did this work. If you go beyond 5 km, most of the cross correlation actions vanishes. That means, urban regions have maximum decorrelation length of 5 km, which is again very critical and challenging. And then what we have found is that why is it happening? So we have taken a cross section, and in that cross section, what we have found is that it results into huge number of pockets. These are essentially instability pockets, and you can see that if you are using multi-layer urban canopy, there is a huge number of pockets, red to blue. That means huge difference is there, and that results into this is more than these two columns. So that really shows that this kind of pockets results into more extreme precipitation at certain locations. Now we'll go more into the climate services. But before climate services part, we all know that urbanization results into further heat wave, extreme precipitation, flooding, etc., and so on. Now, if you look at IPCC, so Tilo is talking about the science part, which is more on IPCC Group 1. Now we are talking more on IPCC Working Group 2, which has a high content statement that says that in urban settings, observed climate change has caused impacts on human health, livelihood, and key infrastructure. And it says also observed impacts are concentrated among the economically and socially marginalized urban residents. That means informal settlements, which says that in urban regions, those who are essentially living in slum areas, which are more affected compared to those who are living in high-rise buildings. The third thing is that infrastructure, transportation, water, sanitation, energy system, everything has been compromised by extremes, which result in economic losses, disruption, services, and impacts to well-being. But if you look at the Indian literature is still restricted to urban precipitation or bit of urban flood modeling, but it does not really tell you how to really quantify. This kind of quantification and solution are still lacking in Indian literature. So, what are the need of the hour to make the urban, urban smart, I would say weather smart urban system? You need in urban region, as I said, that there is a huge spatial variability. So it needs an extensive monitoring and efficient information dissemination. You should have a very early warning system so that you can save people's lives, people's property, save people's time as well. And with hyper local information, you need to go at hyper local because it has very high spatial variability. And you need a specific decision support system so that you can actually take some of the no regret decisions, and then infrastructure planning and so on. The challenges is that modeling and monitoring of urban climate is very difficult. Lack of representation of urban and human component, and finally interdisciplinary approach for developing the decision support system. We are still very much lacking. Not in India, most of the globe is actually lacking this area. So what we did is that very recently, one of the insurance company, HDFC Argo, approached us for developing some sort of a weather smart Mumbai city solution. So we worked on something known as weather smart and climate ready urban forecasting system or something like that. So another thing I'd like to mention is that we know that Mumbai has been suffering because of flooding, but till 2021 there was no flood monitoring system. Even there is some flood monitoring system, but still the data is not available. So let's say on a monsoon day, which normally rains in Mumbai, so if you have to go from one part to another part of the city, and if it is raining, you don't know if any regions are getting flooded or not. So that's not the challenging part. So what we thought is that since there is not, so can we develop some sort of a portal, some sort of a system which will be run by the Mumbai citizens for the citizens. So what we thought is that can we really improve the state of art weather system with some sort of a citizen science. And for that, what we thought is that we'll use the social media to do crowdsourcing as well as local people, local NGOs, and then we'll take satellite image and available video sensors, merge data to get a real-time flood map. Then we'll use science modeling, is regional modeling, then coastal modeling, and then finally we'll all of them together to develop a high resolution urban climate modeling, which will give you the forecasting in one way, and the way it will generate flood and flood risk map, so that we can go for damage estimation. So this is what was our initial plan, and we started working, and we found that it is extremely challenging when you are really working on a operational real life problem. It is very, I mean, it's quite easy to really develop some kind of a model and show some validation, but when it really needs for applications, it's a challenging task. So one thing what we looked at it is that we found that there is absolutely no data is available. So what we thought is that let's start collecting some data. So we started using Twitter, which is presented now known as X. Started it was Twitter, which was free system. So we thought of course collecting data from Twitter. We started collecting data because we wanted to know that if you have to do crowdsourcing, you have to be very sure that crowdsourced data is reliable. So for that we have talked to few volunteers who are actually well trained and they are ready to give us some information, and we'll sort of getting word-wise information. So we trained the volunteer initially to get some information. We created a WhatsApp group. A lot of people were there, and then we sort of getting different information from different people, so that we can keep on updating and see what exactly is happening. So, and we found that this crowdsourced data has a huge some sort of a information system. So let us see. This is one of the days, July 5, 2022, where we have got tweet information like this. We can see this is the region where a lot of people are saying that many regions are getting waterlogged over this region. And when you have checked with the volunteers information, we found the same region where actually a lot of water information is coming. They are matching. Now, when they looked at the rainfall information on that specific day, we found that this is the region which receives very high rainfall. I'll come back to this, why this region is receiving very high rainfall. And this is the region where there is low elevation. So all of them are actually matching with each other. That shows that yes, this is the region which is very likely to get very heavy flooding, and it is actually saying the same thing. That clearly shows that whatever information we are getting through crowdsourcing, they are important and useful. Let us start using them. Once we have that, then we thought that what exactly let's happen from 2017 to 2022. So we wanted to understand what exactly happened. So from 2017 to 2022, when we are doing what we have found is that though the important tweets have increased, the useful tweets, but number of tweets have reduced related to extreme flooding. So that clearly shows probably BSC is doing something because of which the flood situation is improving, because they are for very similar kind of rainfall. So, but there could be another reason, because 2020, 2021 and 2022 is mostly flood COVID affected. So maybe people are not going out, so they are not doing. So for that part, what we did some ground survey. So we talked to different people and we realized that BMC has done a huge amount of work, the municipal corporation. And we found that the regions where actually it has worked, most of the regions, they work quite significantly. So what we did, we talked to the residents over that region who lived there and the shopkeepers who kept their shops open even during the COVID time. Totally. So we found that it really worked. So which was a good thing for us. We realized that tweets are really very useful information. So then what we thought is that then we back to the rainfall. As I said that this is the region which receives very high rainfall. Why is it so? When we looked at it, what we have found is that what is the pattern? You can see there is a horseshoe pattern in the extreme rainfall over Mumbai. Why is it so? Then what we have found is that if you consider the elevation, this is the high elevation region, Sanjay Gandhi National Forest, and this is the low elevation region. So when moisture comes, there is some sort of orographic thing that is happening that results into heavy rainfall over this region. The heavy rainfall is happening over low elevation region, so that will result into flooding, and that's the Mumbai city. And then what we thought is that we have to understand the spatial variations of Mumbai rainfall. Let us first the clustering. First we clustered similar kind of stations under each class, so that for each of the class we can do a good downscaling that can be representative of all other classes. That we did started using some AML approach. So what we did is that we have considered the observed rainfall, and then we have considered the global force model output, which is known as GFS output. And from GFS gives typically a 50 km resolution for NSET from NSET. So we took the NSET GFS and then started downscaling it with a CNN method, convolutional neural network. So the idea was that can we really improve at a station level, at a very high station level we are trying to do. And what we have found is that for instance it's not working. So then what we do, we use some method which is known as transfer learning. We took the same model but do a special training on the extreme days, which are limited number of days. And then what we're trying to do is that if GSS says extreme days, then we are using that transfer learn model or otherwise general model. And then we check how is it working. This is done by one of the student Puja Tripathi. And this is considering the original forecast system. If you consider the heat rate, how many times the extremes are correctly forecasted, you can see that with GFS the heat rate is quite low. When we are using CNN based downscaling with GFS, then they are improving. But as you are using transfer learning based CNN, you can see the heat rate is as good as 80% in many locations. So it is significantly improving. Second thing is false alarm. How many times it produces extremes but it's not actually extremes. GFS has high false alarm, which is bad. CNN also has reduced little bit, but if you consider the combined model, which is a transfer learning model, it has reduced quite significantly. So that clearly shows that after doing a proper machine learning kind of thing, it is actually improving. Once we have this, then we thought that we are getting a lot of rainfall information. Now let us install some sensors. So two of our postdocs, Mayan Gupta and Aniket Nalka, so they have done a huge job of sensor installation, which is a very easy thing. Because when we are doing a sensor installation, we make sure that security TVs, everything is there, because we are putting it in one place and there may be vandalism, there may be something or other will happen. So what we did, and we also found the electricity and structural support. So we started talking to local people and multiple visits, talking to the engineers, take some feasibility study, getting NOC. If it works, then again go back and again talking to stakeholders. So it was a multiple iterations, and finally getting official permissions and then going for sensor installation. So it was a very difficult task, but they task and they have installed a few sensors over this region. Our team has sensors to get the real. So it shows something like this. You can see lots of ups and downs is happening because under the sensor is high, so there is some signal or something. But you can see when there is rainfall, it immediately shows that rainfall is happening. Things are getting waterlogged. So this is at Pakula Nala. This is another canal sensors. This is for Mithi River. You can see that the rainfall, how the things are actually increasing, water level is increasing. So that clearly shows, and this can be a very good validation data for the extreme flooding. With this, what we did is that our team has developed a Mumbai flood app, which is used for forecasting system. So our plan is next season will make it 3 hourly rainfall forecast, but last year we have to 3 rainfall forecast with daily rainfall forecast. And so this was an Android app which is available, as well as there was a website which was available during the monsoon. Only keep it during monsoon, because non-monsoon there is no rain. So only during monsoon this website will be available, which will give you 3 days near real time hyperlocal rainfall forecast. It will give local train information at railways, what exactly is happening. It will give you the water level wherever we have installed the sensors, and also it will also collect a lot of information from it, and it will keep on providing to the giving it to the people. And also at the same time, whenever people are giving their information, so that will be automatically updated. So essentially, a person who sees flooding is happening, they can give information through this app. Immediately other people can see. So it is the way like citizen is actually helping citizen in terms of providing the real-time information. So Mumbaikars can report waterlogging through this app, and immediately it will be available. So this is some sort of a structure you can see here. So let's say this is one of the stations. Just a minute. Yeah, it should work now. So, I know somehow it's not working. Give me a minute. Just give me a minute because this is important. I need to show this point, but somehow it's not working. Let me just.
So please say that again.
Yeah, no, that's fine. I have another video which I'll just show. Yeah, so I think I'm there. I'll just switch the sound and I'll show it. Can you see this? Yeah. So this is one of the app which is being designed. Uh, yeah. So essentially, you can see here. So these are essentially the stations. You can pick up any of the station. Let's say if you're picking up one of the station, what it will give you is that at present, what the last 12 hours, what was the rainfall value at every hour. Then what was the forecast for next 3 days, and how did it perform over the last 3 days. And one thing also we wanted to show is that how the model has performed over the entire season, because a person only believe this forecast if they will see that how did it perform over the last few days. the season. So this is what it actually gives. You can see hourly rainfall observations, 3-day rainfall forecast, and how the model perform. Now this is something which is very important. It shows that let's say someone is finding his region is waterlogged. He has to give this information for others to use, and this is known as crowdsourcing, bringing citizen science. So let's say someone is giving correct locations, giving his or urban height, and giving the waterlogging condition. So essentially, go back again. So let's say someone finds there is a knee length of water, providing his or her own height. Then click on knee length of water, select the location, and making it okay. Immediately it will be visible on the web app, and others will be able to see. Now, this is the Android version which we have considered, and the Android version also you will be able to see exactly the same thing. Now, this is about the sensor data. So you can see that these are the sensor locations where you can actually click on the sensor locations, and as soon as you click on the sensor locations, you will see that on extreme day, for example, how the water level has increased over these regions. And these are of course the sensors. So this is all what I have done. Now I will go back to the presentation. And if you can see that for the last, yeah, hello, can you hear me? Yes. And when you looked at it, how did we perform? I am specifically showing because this year, the option forecast of the government agencies have been highly criticized. But for this specific season, except just one extreme event, for all the extreme events, it performed very good, and it has been correctly forecast. For example, one of them on 20th July, where it is very high rainfall, and it has been forecasted correctly this extreme rainfall. The other one was 25th September, where there was extremely heavy rainfall, more than 200 mm rain in just few hours, and you can see that this was correctly forecasted where all other models failed. So that shows that this model is actually working quite well, and this is what we have done. So this is starting from 1st June to last day. So how did we perform? And as I said that we have missed one of the extremes. So this is one extreme that we missed completely, and other than that, for most of the extremes we could forecast correctly in this season. And this was available last season, all the Mumbai. Around 2 lakh people actually check this website. And at the same time, we are also doing some tweet analysis. We are every day we are providing with what sort of information people got about Mumbai floods, whoever was positive and whoever was negative, we did something. And also during the extreme rainfall, we showed what railway line is Mumbai's lifeline. So what are the stations which are waterlogged? We are trying to give that information in terms of how much rainfall is happening. Let's say in our 20 or more rainfall is happening, people say that region gets waterlogged. We are trying to even get this information as well. And after that, it got a huge coverage because it was actually helpful for people, and we realized that a good system actually works if you bring citizen science specifically for the urban region. So this is our team who have actually worked on the urban flooding. Yeah, so that's all from my side. Thank you for your attention, and if there is any question, I'll be happy to answer. Can you hear me?
So we will have questions. There are students coming in and asking questions.
Yeah.
Good afternoon.
Good afternoon.
So, sir, you said the app detects, like we can put our input that I am height of a person, height, and
Can you please repeat your question? Sorry, I didn't get.
Sir, you mentioned in the app that like we can put our input that this height person and the water is at this right. I can give my input to the app. So if there are people who are sitting with the app and putting wrong input, are there
background fact checks again before putting it on the app?
It's impossible to perform any kind of quality control, but the idea here is that we believe that people, most of the people will give correct information. So let's say there is an outlet. So let's say if there is a region which is waterlogged, and let's say 50 people say yes, it's waterlogged, and one person says it's not waterlogged. So then it's quite clear that one is essentially the outlier. So the idea here is that this kind of system will only work there are more participants, and we believe that most of the participants are honest. There will be few who may give inadvertently or intentionally wrong information that can be ignored. So that's the way it should work, but we have not used any kind of quality control at this moment. But that's an important thing. Also very difficult to do it at real time.
So, will the act in future steps to make it quality control, and they could fact check before putting it on? Like if it's only one person.
You can't do that. That's problem, right? You cannot make it real time then. If you are performing an analysis, it will take some time, right?
Yes.
The first part information has to be provided. So we have to rely on people. But what I found is that people don't give random information. Most of the cases, we have not found a single case where there is random information in the last season, which is very interesting.
Yes, sir. Thank you.
People generally want to help people, and this is not associated with any kind of any government agency or anything. It's a completely independent body, and where we say that run by citizen for the citizen. So people are kind of honest. So they don't have any other hidden agenda or anything. So which was actually good. But a quality control is important, but how to make it in real time is a big question.
Yes, sir. Thank you, sir.
Good afternoon. Good
Yes.
afternoon, sir. In the first project where you compared the precipitation pattern of Alibag and Mumbai, you did a PCN cluster analysis. Sir, may I know what are the parameters that you used in PCA and what are the parameters that came on the top that actually controlled the urban precipitation change in Mumbai?
This is not precipitation change. This is for understanding the circulation patterns that results into extreme precipitation over the region. So what we try to do is that we try to cluster FDS weather pattern. Okay. So let's say a specific weather pattern can be given by U wing, V wing, the moisture, the temperature, humidity at different levels, potential height. So consider all of these variables, and they are highly correlated with each other. Just to reduce the dimension, we have done the principal component analysis, and then we perform the clustering with those principal components to understand if we can classify the days based on weather circulation pattern. And if we have classes those days, then we can find out that most of the extreme days belong to one class. That is the so that day's circulation pattern of that class, the circulation pattern associated with that specific class is the extreme circulation pattern. Okay. That's what we have done.
Okay. Majorly the components are not morphology, but just
no. They are the circulation. So we wanted to understand which circulation pattern results into extreme precipitation, and then we are trying to find out that if the extreme precipitation to those circulation pattern are they different in Mumbai, Alibag, or same. If urbanization doesn't play any role, then they have to be same. They are different, and their changes are different because of urbanization.
Okay. And in Mumbai, what are the areas that you did, you considered for the analysis? Is there certain areas in Mumbai that you considered for the analysis?
Yes. I have shown that horseshoe pattern. Those are the regions which is normally very high rainfall in Mumbai, and those are also the low elevation region because those are around the Sanjay Gandhi National Park, and those are also low elevation region. So they are prone to extreme flooding because of heavy precipitation and low elevation, and also close to the coastal region, of course.
Okay. Thank you, sir.
Thank you.
Good afternoon, sir.
Good afternoon.
Sir, it is is a natural tendency of human beings that whenever they settle at a particular place, they do try to expand their territory. And as we are moving forward with time, the urbanization is a necessity and it is a must for human beings. But on the other hand, urbanization is directly and adversely affecting the climate change. So my question is that it is possible to occupy urbanization in such a way that it does become climate friendly.
Yes, that's what we call it now, urban planning. We are not talking about random urban planning nowadays. So whenever there is an urban planning is happening, it should be sustainable. So it should be whether smart and climate ready or climate smart, whether it is whatever term you use, it has to be like that. Otherwise, there will be problem. That's what we are facing. So I mean, most of the existing cities are not climate friendly. That's why there is a lot of pollution, etc. But I hope the new cities will follow certain guidelines or do an extensive study with urban microclimate and so on, so that they will be ready for the climate change. Thank you.
Thank you so much, sir, for joining and giving a very valuable research that you have been doing and sharing it with our students and participants, and also setting the tune for our course for 5 days. Thank you so much for joining.
Thank you. Thank you very much.
Okay, so now we will head to Department of Architecture for registration, and also all the other lectures, tutorials and practical sessions will be taken up will be conducted in Department of Architecture and Planning.
We need just to see the topic, for us.
Because me and like Dr. Soumya take the chance only. We are working on climate change, flood, droughts, and hydroclimate extreme events. Even we can include in some of the papers.
If I can help, yes. learning and show. It's okay. I help you. It's my lecture, so.
It's our responsibility for the
स्टार्ट हो गया क्या?
Professor Rafiq Hamdi began his academic journey in 2000 with a civil engineering degree in meteorology, followed by a master's degree from Catholic University of Louvain, Belgium in 2002. After completion of his PhD in urban meteorology in 2005 from Institut d'Astronomie et de Géophysique (JSGMAC), Professor Hamdi has been an integral part of the research department at the Royal Municipal Institute of Belgium. His work with the international consortium GIAN, specifically on the development of Alaroth atmospheric model and the surface land surface scheme, has been groundbreaking contribution to both numerical weather prediction and urban climate modeling. Professor Hamdi is also a member of prominent international organizations, including the International Association for Urban Climate, IAUC, and Urban Climate Change Research Network, UCCRN. He further served as a lead author for Intergovernmental Panel of Climate Change 6 Assessment Report IPCC AR6 in 2021 and the Summary for Urban Policymakers SUP IPCC report in 2022, demonstrating his pivotal role in shaping global climate policy discussions. Beyond his research, Professor Hamdi has been deeply committed to academia, serving as a guest lecturer in Ghent University since 2014 and a guest professor at the Chinese Academy of Sciences since 2023. His mentorship of PhD, master's, bachelor students highlights his dedication towards nurturing the future leaders in climate science. Professor Hamdi's extensive body of work includes securing funding for 13 research projects, co-authoring more than 100 peer-reviewed publications, and contributing to 20 book chapters. His expertise has also been recognized in practical applications, such as his role as an urban climate expert on the scientific committee for the 2024 Paris Olympics. Today, we are privileged to have Professor Hamdi with us, who has traveled from Belgium to share his unparalleled knowledge and insights. His work on regional climate modeling, urban meteorology, and the impacts of global warming on urban environments is invaluable as we confront the challenges of a rapidly changing climate. It is both a privilege and an honor to host a distinguished scholar and a globally renowned expert, Professor Hamdi, whose contributions have significantly advanced our understanding of urban meteorology, climate modeling, and the critical dynamics of urbanization and climate change. Sir, I would request you to please address the gathering.
Thank you very much for the very nice introduction, and good afternoon, everyone. Good afternoon also to the online participants who are joining us also. So I am very honored, and I would like to thank again Professor Surabhi for her invitation, very kind invitation. So I am deeply honored to be here for the first time in India. So I am happy to explore also India and also the wonderful people that you are. So my lecture will be this afternoon divided into two parts. So the first part, because I discussed a bit with Professor Surabhi, we said, okay, maybe it's good that we give you like a general introduction. So what is climate change? What is this problem from the beginning? Then in an easy way. And then the second lecture will give you what is the state of the art, what we know now on climate change from the latest report, IPCC report. So here it's my first lecture, so it will be 1 hour, then we take a break, and then we go to the next lecture. Okay, so yes. So maybe next slide, please. Yes, so the first thing that I need to say is that the climate is very complicated. It's really a complicated discipline because you need to know meteorology, you need to know oceanography, physics, glaciology, biology, mathematics, numerical modeling, because you need to run with supercomputers, so you need to be very good in this, and also how the infrastructure is evolving. You know that now we are moving from CPUs to GPUs, so some code that we are using is no more adapted to GPUs, so we need to adapt our code. Very, very, very important. Economy and technology, because this is related to your question, how in the future the economy will change and how this will change urbanization, how this will change the behavior of people. So you need to link economy, technology, socio-economy also. So all these disciplines you should to know to make the good scenario projection in the future. And how this affects the emission, you will see. So climatology is an applied science. So it's not an exact science because you need to know all this and you put this all into one, you combine all this. So what I would say is that no one can master this. You can never find one person who is able to do all this, including me. So it's normal that if you ask me a question, maybe I will not be able to answer because maybe this question is related, maybe your question is related to this. I am not expert on running this future projection. I just use this future projection. maybe you have question glaciology, but I am not expert on glaciology. So you see, it's really very difficult matter, this climate. Next slide, please. And the most important is that climate change is a hot issue because we need to provide guidelines to policymakers. Policymakers, they are, this is what has been said this morning, they need solid science from us for the policymaker. And also, the policymaker, we need to change our way of talking with the policymaker. It's not that we scientists, we have the knowledge and we give this to the policymaker. It is not working like this anymore. We need to set up a dialogue with them. This is what has been shown in the lecture of Professor this morning, Subal, yes, about how they involve stakeholders in the map. Did you see you remember the map that the application, the application that he showed? He said that there is a feedback and interaction with the stakeholder. It's not only one time. You need to set up the dialogue and then interact with the stakeholder because they might need some information that from you. You don't know that this is important, so you don't save it in your output. But then later, it becomes important. So it's a dialogue and it's an iterative dialogue with the stakeholders in order to. And you need to start from the beginning. So it's not that you are doing your research in your corner and then you said, look, I have some. No, it's not working like this. For climate, you need to involve all together from the beginning. Next slide, please. So let's start from the beginning. So why we have this? What is the climate? What is happening to the climate? So the climate. So the Earth, the climate of the Earth is what is influenced by the forcing. Okay, so we have the forcing, and climate forcing. What is the most important is the radiation. Okay, so the radiation which is coming to the Earth is the only way the planet interacts with the rest of the universe. So it's the radiation. So this radiation is then converted to heat. Okay, and then this heat is then converted to kinetic energy, which is momentum, so the wind. Okay, so the atmosphere can be seen as an engine, or if you wish, you can call it a heat pump, and this is explained by the general circulation. So you have the Earth, you have the radiation which is coming, and this radiation heat the atmosphere. The atmosphere is circulation. We call this the general circulation, okay, which include like monsoon, also, and all this stuff. This is general circulation. So the climate can basically change for two reasons only. The first one is change in the incoming radiation. So this radiation change. If the radiation change, okay, the climate will change. Or a change in the mechanism for the energy conversion. I told you, radiation converted to heat, heat converted to general circulation. So if this mechanism change, then the climate change. So the only two ways the climate change is radiation or change in the mechanism. Next. So what is so you all heard about this greenhouse. What is the greenhouse effect? So I will start from the beginning. Then we are all clear about what is greenhouse, what is this problem of greenhouse. So suppose that there is no atmosphere in the Earth without any atmosphere, and with an optical thickness, the terrestrial radiative emission should be equal to the absorbed sunlight. Okay, so this is the radiation that we get from the sun. Okay, so you remember here P R is because it's spheric, because the radiation on a spheric is this, and this is the radiation. This is the constant, and this is the albedo. I will explain what is the albedo. And this radiation should be equal. What is this? This is the emitted. It's the Stefan Boltzmann emission. So this is like if you have a black body, this is how it will emit radiation. So this is how. So if this is the Earth, temperature of the Earth to the power 4. So if there is no atmosphere, the radiation that will come will be output by this law. That's very easy. So if you compute this is the constant solar radiation constant. This is constant. You will see it has a cycle of 11 years, but we can consider it constant. And this is the albedo. What is the albedo? This is 0.3. It means if you have solar radiation, part will be reflected. Part of this solar radiation. For example, if you have a snow is white, a lot of radiation will be, so this is the albedo. Albedo of snow is very high. But if you compute the albedo of the Earth, is 0.3, okay? And TE is the effective temperature of the Earth, okay? So the solution of this is very easy. You will find that temperature is 255, which is about minus 18. So if you don't have the atmosphere, the temperature will be minus 18 degrees. So, but hopefully we have the atmosphere. That's why we cannot live with this, on average. Can you go to the... So why we don't have minus, why we have, the average temperature is 15. So why we have 15 degrees on the Earth? Because of the atmosphere. The explanation lies in the optical thickness of the atmosphere, this heat the atmosphere. So you have the atmosphere, and this atmosphere heats the Earth, and then we have a temperature of 15. So it's a greenhouse effect. So the greenhouse effect in the atmosphere is a changing in the radiative equilibrium. So remove the atmosphere minus 18 degrees, put the atmosphere 15 degrees. So you see, it's a greenhouse. So the greenhouse changed the radiative equilibrium of the Earth. Next slide, please. So the radiation basically, so I will not enter into details, but just general. The radiation, you need to think of two types of radiation. These are the most important. You have the visible and you have the infrared. We call this mid-infrared. So the visible is this, like during the day, the sun radiation. The radiation, this is visible, okay? So it is in this band. This is the spectral band of this radiation, visible, like today, in the day, you have solar radiation, visible, in the visible, mostly in the visible. During the night, when we have Earth, cooling of the Earth, this is more infrared radiation. So put it in your mind. In the short wave in the day, infrared mainly in the night. The most you have also in the day, but the most important is in the night. Next slide. So this graph, what is this? So here in blue, this is what is this long wave emission. I told you, in the night, you have long wave emission from the Earth. So the blue is what is emitted. This is the radiation which is emitted at the surface. So at the surface here. And in red is the top of atmosphere, top. So you have the atmosphere, you have and then you have the top of the atmosphere, okay? So we compare between the surface and the top. You see that here, that's more or less okay, but here you see that we have reduction. It means that it's absorbed. So this is absorbed by CO2. So CO2 absorbed in this band, in this band, CO2. You see a little bit also here, water. Water is a greenhouse gas, water. You have also ozone. In this band, ozone absorbs a lot, but it's more higher, troposphere. Okay? So the greenhouse gas, because we always talk about water vapor. We always talk about carbon dioxide. We say carbon dioxide is greenhouse gas, but the first one is water, in fact. The water, and then carbon, and then other gases. So next slide, please. So now let's look to the visible. So during the day, short wave. So this is the shortwave radiation, and this is the altitude. You see here, 10 kilometers of the atmosphere, 10 kilometers, and then you go up. So the blue is for the water. You see that the water here is absorbing. So this is at 5 kilometers, you have maximum of absorption. So this is how much degree per day. So the water is absorbing the visible. So it will heat. Okay. Now look to the CO2. CO2 is in green. So the CO2 does not change. So it means that for the visible, the visible radiation during the day, for example, when it is coming to the Earth, okay, the CO2 will not affect. You see, CO2 is exactly the same. So the radiation will not change. So it will not heat the atmosphere. The CO2 is what we call here. So different CO2 is transparent for light. So if you have light coming, the fact that you have CO2 or not will not change the atmosphere because CO2 is transparent for light. Okay. Next slide, please. Okay. So now, so we say that we have this increase of temperature which is due to the greenhouse gas, but it is generally believed that the increase in temperature depends logarithmically on the concentration of greenhouse gas. So here this is the like the concentration or initial concentration, and then you increase the concentration, the temperature is a logarithmic way. So it means that it will increase this way. It means that since it is logarithmic, the more you add greenhouse gas, the temperature will not warm that lot. So one could say the more we add greenhouse gas to the atmosphere, the less they will have a greenhouse effect. Normally, this is what should happen because it's logarithmic, okay? But in fact, the sensitivity without feedback of carbon dioxide is about 1.3. So in fact, if we don't consider the feedback, okay, if we just add a greenhouse gas to the atmosphere, normally if you add, your atmosphere, you will heat, the temperature will increase by 1.3 degree. Okay, but this is not what we are observing. So because you have feedback, and I will tell you what is this feedback in the next slide. So the sensitivity, so just put this in your mind. The sensitivity without feedback is 1.2 or 1.3 degree. Okay, so why we are talking about climate change and the problem of climate change? Because it's only 1.3, but no, because there is feedback. The feedback you will see, which will put the warming much more than 1.2. The next slide, please. So, of course, in the atmosphere, we have the feedback. This is what I told you. And one of the feedback is the urban. You have the surface that have a feedback with the atmosphere. And you will see this is for the urban is one example. So the net sensitivity is not 1.2 or 1.3 because of the forcing, because of the feedback. If we don't have this feedback, we don't have any issue with climate change. But because of this feedback, then it becomes really an issue. Next slide, please. Okay, so one of this feedback, it's the surface feedback. So because the surface, here if you have vegetation or if you have city, the surface is interacting with the atmosphere. So this interaction is via some exchange. So you exchange water, you exchange heat between the surface and the atmosphere. So this make a loop. For example, I will give you an example. So suppose that you have a warming over warming so the temperature increase. Okay, this temperature increase will make a lot of evaporation. Okay, from the soil because temperature increase. So more evaporation. This will make your soil dry, right? So the soil will be dry. So in the next step is that the soil, since it is dry, it will be warm because you don't have evaporation to cool down. So the temperature will be more warm. And then this is the loop. You see? This is the feedback. So the feedback will with the surface. Next slide. So yeah, this is what I already said. The surface absorbs and reflects sunlight, and it also emits long-wave radiation. This is we know. And the reflection is called the albedo. So this I told you about this. And yes, so this is just to give you some. So this is for the average, and you see here, for example, the albedo that I told you with the surface. For example, for snow, it's different between old and fresh. You can have the fresh, very white. You can have 0.8 albedo, while the old one 0.4. So it's a feedback, because if you have a warm temperature over snow area, it's not the same like you have a warm temperature over a dry area. Because also if you have a more solar radiation over snow, it's not the same like you have more solar radiation over a dry area, because the snow will reflect. So the snow will reflect, so you will have different process over different type of area. So that's why the surface feedback is very important. It's one of the feedback that it's very important to take into account. Next slide, please. And yes, and another type of feedback is, because it's about urban, is the urban heat island. Because the fact that you have city is different from the fact that you have a rural area or forest. One very unique aspect of city. What is the very unique aspect of cities? That you don't have anything. Yes, but you can say, but for the atmosphere. What is unique that the city is giving to the atmosphere, which other type of surface is not given to the...
More favorable surface, so it reflects the radiation.
Yes, all this, but it's the anthropogenic heat. Yes, the anthropogeny. Because you can have, for example, you can say, okay, city is affecting the wind, but forest is also high, so the wind is also will be reduced. You can say city is warm, but you can also have, for example, during the night, water body is also warm than the dry. But the unique, very unique, that you don't find is the anthropogenic heat. You don't find this in forest or in lake or so. So this is very important. So all this feedback should be taken into account for the. Yeah. But this I will, because the urban we will have this more and more. All this I will not go into detail in the urban. Next slide, please. Yes, the other feedback. So we said the feedback surface. Okay. The other feedback is the aerosol. What is the aerosol? Do you know what is aerosol? You know what is aerosol? Yes. Yes, so the aerosols are these particles that are suspended in the air. You don't see it, but they are here in the air. And this can be dust, sea salt, soil particle, volcanic, pollen, etc. And you see the size are very small, very, very small. And they are almost, but what is particular in this aerosol, they are not staying in the atmosphere for a long time. The CO2 has 100 years flies. But these aerosols, 3 days, they stay 3 days because they are coming back by rain. So they don't stay in the atmosphere, and we call this what we call it's here. It's short lived. So it should be somewhere here. So we call this short lived because they are not in they don't stay in the atmosphere for a long time. Okay, and they are very important because they form the nuclei for the cloud formation. So if you don't have aerosols, it will be difficult. That's why we heard this morning about the effect of urban on precipitation. One of the effects, Professor Subimal showed this, is the aerosol. Because the aerosol can increase the precipitation. Because you have more aerosol, you have more precipitation. So the aerosol is very important. Because yes, they are very important also for radiation, for absorption and scattering. Because if you have aerosol, and you have radiation, the fact that you have aerosol will impact the absorption and the scattering, okay, of the radiation. For example, but we will see this, I think, in the next slide. Yes, next slide, please. Yes, here. So this is to measure how much of aerosols. We call this optical depth, but don't worry about it's just a measure of how much we have aerosols in the air, and this is in Uccle, in Brussels, okay? And this is from 1982 to now. What we saw is that there is a decrease of aerosols, okay? Because of all this air pollution condition, so we limit the emission, etc. So we have the aerosols which decrease. So if you have a decrease of aerosols, and you will see in the next lecture, normally aerosols make a cooling of the atmosphere, and you will see in the IPCC that the aerosols make the atmosphere cool. So it's a cooling of the, it's not a warming. So with this decrease, in fact, we found that, for example, in Europe, the summers of Europe are more and more extreme because we have less aerosols, then you have more solar radiation coming to the ground. Because less aerosols mean you have more radiation and if you have more aerosols, you have less radiation because all is scattered, so less radiation, so it's cooling. It's cooling the surface. But we found that over Europe, for example, the fact that we decrease the aerosols is good for the health, but it makes the summers more and more extremes in Europe. So it's kind of, yeah. Next slide, please. Okay, so if the atmosphere increases, there will be yes, the other feedback, so we call the surface feedback, the aerosols, and the other feedback is with the water vapor, or what we call the cloud. It's very important. The fact that you have cloud will change everything. So if the temperature increase, okay, then there will be an increase of water vapor in the atmosphere, okay? So if you increase the temperature, you have more evaporation, so you have more water vapor in the atmosphere. So we saw that the water vapor is a greenhouse, right? We saw this I show you this. So if it's a greenhouse, so it will make more hot. So if this water vapor does not condense to form cloud, if it stays water vapor, then it will enhance the greenhouse effect. Okay, and this in turn will enhance the temperature and so on. So you see the feedback. So you have a warm, temperature, warm temperature, more evaporation, so you have more water vapor in the atmosphere. This will be more because it's a greenhouse. It will make temperature hotter, and you see this is a feedback also. So you remember that's why we don't have 1.2 degrees Celsius of, this is without feedback.
So, sir,
Yes?
it is beyond going to 1.2 to 1.3, so that will create a problem, or it is a standard? That you have said that the feedback 1.2 degree between 1.2 to?
Yes, normally this is without all this feedback, yes.
So it is, I think it is a standard atmospheric regular procedure.
Exactly,
like
yes.
System.
Yes.
So what will the problem arise? Beyond the 1.3 or?
No, this is the 1.2 or 1. This is if there was no feedback. This is just a theoretical. We say, okay, if we have an atmosphere where we put more greenhouse gas, what will be the temperature? Will be because it's logarithmic. But the atmosphere, it's very complex because you have all this feedback that impact the temperature. So it's not only adding greenhouse gas warming, but this, for example, if you warm, the process will change, all this feedback.
So any standard, natural standard of the temperature about, like you said, 1.2 or 1.3 or beyond that? You know, I mean to say, lots of anthropogenic activity is going on in
Yes.
cities and urban
Yes.
areas.
Yes.
So nature has itself any specific temperature to
The next equilibrium.
type of activity.
Yes. This is what we will see in the next slide. So what is the next? What is the equilibrium state that we will reach? Yes, this we will see in the yes. So yes, okay. Yes. So this is, but this matter that I show here with the water vapor it will be more complicated if you have cloud. This is just without cloud, because if you add cloud, then the amount of solar radiation will decrease because you have cloud. So less solar radiation will. So it's much more complicated. But yeah. Next slide, please. Okay, so yes, then you have cloud feedback and aerosol. So the cloud feedback can both be cooling or warming. Yes. So for example, I give you an example. During the night, if you don't have cloud, okay, the night will be cool. Why? Because all the infrared emission can go to the air. Okay. Yes. So cooling, you have a cooling. But if you have cloud during the night, a lot of this infrared will come back because they are reflected by the cloud, okay? So your night will be not that cool, will be not that cold because you have the cloud feedback. So you see, or it can go to cooling. For example, during the day, if you have cloud and you have solar radiation, so you have less solar radiation because it's cloudy, of course. So then you have less temperature during the day. But if you don't have cloud, like today, then it's warm. But if you have cloud, it's cold. So you see, the cloud is different. It can affect in different way. So that's why we need really, for all the atmospheric model, the climate model, we need to have a good parameterization of microphysics. So if you have a good parameterization, then your model is good. So here is all the feedback, but I don't want into. Next slide, please. So this is why we need what we call AOGCM. This is Atmosphere, Ocean, Global Circulation Models. Okay? So you need, if you would like to study the climate, you need atmosphere and you need the ocean. The ocean is very, very important also. And then we can reach, if we have a good model like this, then we can reach what is, if we put more CO2, what will be the next radiative state? This is your question. What will be the temperature? So, but we need to have a good model first that take this into account. So this is what I say. The sensitivity without feedback of CO2, if you change only the CO2 without any feedback, is about 1 to 2 degrees, okay? But in reality, the sensitivity will be different because, and the problem for this are the feedback that I just explained you between the surface, aerosols, cloud, all this. Okay, so the only way really for now to estimate the net sensitivity, your question, is to include all the process that we know into the model, into the atmosphere and the ocean, and carry out sensitivity tests. So we try to have the best model we can have. We put all the process that we know, and then we run the model to see what is the next state. If we add more CO2, what will be the temperature? Because we know that this is not good. This is not correct. Okay? So this is why we need this atmospheric ocean general circulation model. But here in these courses, I am not expert on the ocean. So you see, already I told you, you need to be expert on ocean. I am not expert. So we just use the model. But here we will focus on the atmosphere. Next slide, please. So I will not enter into detail. These are the equations that what we call the primitive equation of the atmosphere. Okay, so you need to understand all this, and we put this into numerical model. So that's why I told you you need mathematics and physics. All this is mathematics. And next slide. So what we do, so here, for example, is the Earth. We try to make a grid over this Earth. Okay, so like all these points here are the grid point. Okay, we have a mapping of the Earth. And you see that since we will have a mapping over all the Earth, the resolution, what is the resolution? Is the distance between 2 points. Distance between these 2 points is the spatial resolution, let's say. So since it is very, of the Earth, normally it's very coarse. So for example, now I will show you the model of IPCC, which resolution, but it's around 100 kilometers. You see, 100 kilometers is too coarse. You cannot, city, for example, the cities, they are not seen by the global climate models. I will tell you about this. So, and then we discretize. So all these derivatives that I show you, the derivatives are replaced by finite difference or other method. You see here the numerical technique is very important to put all this equation into a model. You need to know, is it this? This is the numerical technique, which are now very challenging because I told you we are going from CPUs type of computing to GPUs, graphical. This is the new way of doing the computation. So all the method that we make until now should be adapted to this new. Next slide, please. Okay, so you have a mapping over the Earth surface, but you need also the vertical level. Okay, so you need to map to have a vertical level all over the atmosphere. For the moment, we are having, like, for example, 100 level. And it's better if you run climate model to have a lot of levels near to in the boundary layer, like from 0 to 3 kilometers. It's better to have a lot of, as much as possible, of atmospheric level, because then you can resolve all the process that are happening in this. So here we are using this type of variable of sigma. So you see our this variable that we are using, it follows the surface, but then upper air it's constant, because that's why we assume that in the upper we don't have enough process. So but in the surface, so it's following the surface. It's very important that your variable, that your layer is following the surface, that you can understand orography, all this aspect of the surface. Okay, next slide, please. Okay, the third one is the time stepping. Okay, so the first one is the surface grading, the vertical, and then from one time step to another time step. So this is very important. So you need to have a initial condition, and a boundary condition, and the most important is the stability. This is very important criteria, and I will tell you why. Because you need that you satisfy this, at least. What is C? C is you can consider it like the speed of one process, of one phenomena you are interested on, okay? Delta T is the time step of your model, and delta X is the spatial resolution. So you need to satisfy this. That's why, for example, it will be good if we can run the global model with very long time step. It's much more easy. Then it's very fast to make the computation, to finish the computation. Just to give you an example, one global climate model needs 1 year of run to do the IPCC runs. So you need 1 year, really 1 year of running. So you see, it's very time consuming. Why? Because your delta T must be less than 1 delta X divided by C. Delta T must be small, because we are always, I would like to run with a time step of 1 hour or 1 day. But because then it will, because all the grid points I show you, you need to run your model for all the grid points that I show you, and also all the vertical level. You can imagine the number of grid points that you will run. So the the longer time step, the best. But we cannot because of this condition. So the time step should be less. If not, your model will crash. Your model will not work. So this is also very important. That's why it takes time. Computing simulations really take time. Yeah. Okay, so you have your dynamic. We call this the dynamic model. Okay, the wind you put all into. You have your grid, your vertical, but then it comes all the physical parameterization. So you need to put all this physical parameterization in your model. So this is what I told you. In order, if we would like to estimate a good feedback that I told you, you need to have all this feedback: radiation, convection, turbulence, all this, surface interaction, urban here. Also, you see, I put urban. Next slide. Okay, so and then you have another problem, because I told you, global climate model, you need to run over all the Earth, and the spatial resolution is very coarse, 100 kilometers, for example, for the moment, 100 kilometers. Everything which is within the 100 kilometer, this will not be seen by the model. Okay, so that's why, if, for example, someone is interested by cities, okay, and then go to the global climate model, CMIP6, for example, CMIP6 will not give you what is happening in Bhopal, because they don't see Bhopal as a city. They see maybe Bhopal, maybe it's lake, maybe it's a forest, or because they don't see what is happening. So it's very difficult to get useful information from global climate model for a city, because the city is very. Do you know what is the percentage of city, of urban area in the Earth? Give me. How much you think the city, the urbanized area, are on the surface? What is the percentage?
3 to 4% area.
How much?
3 to 4% area of global.
Yes, less than 2. Less than 2%. You see, all the cities is less than 2% of the surface. So the global climate model, they don't care about cities. We don't care. It's less than 2%. We will not put anything because they don't care. But we are all living in cities, so we need to know, and the stakeholders need to know impact of climate change on cities. So it's difficult to get this information because of this problem. Next slide, please. Another problem is the deep convection. The deep convection, because you have, this is very important, precipitation, intense precipitation also. Like global climate model cannot see this because it's 100 kilometers, and this is really much more less. So you need to parameterize this. You need to add all this. You need to estimate the impact and put it into the global climate model, because the global climate model have a coarse resolution, this climate. Next slide, please. Yes, maybe another example. This is for city, just to give you an example. So suppose that this is how your model, this is Belgium. Huh? Belgium here, you have London here, UK, Paris, and this is Belgium here. So we are running at 4 kilometers, because then your model can start to see the cities, okay? This is not a global model. This is a local climate model. I will tell you about this later. So, but then this is how much of calculation you need, okay, for this domain. It's 4 kilometer domain. Now, if you would like to see this city like this, you need a computer 10 to the power 10 faster. Why? Because the time step, see, the time step should be much more less because you are running at high resolution. So the time step is much more less because of the condition that I told you. If not, the model will not. So you see, you need a computer much, much more powerful. But we don't have this for the moment. I just put this 10 to the power 10 faster, and we cannot this. So that's why we need to parameterize. Next slide, please. We need to parameterize, but this I will explain you this, I think tomorrow or the day after tomorrow, how we put cities into the model. So you can go to the next slide. Yeah, this is how we parameterize the city. So it's really like a canyon, but I will explain you this later. You can go to the next slide. So, okay. So you have all these global climate models, okay, but the problem is that I told you subgrid process. The subgrid process, like convection, I told you, like urban area, like everything, are not solved by solving the equation of the nature that you have. So they are estimated. All these subgrid, they are estimated, okay? And these estimates involve some parameters that have no equivalent in nature. For example, what has been shown by Subimal this morning about the effect of CT on precipitation. They found that when they put multi-layer, it's linked to the turbulence. The CT will make turbulence, and this turbulence, okay, will interact with the wind, etc., and will make the precipitation correct, intense precipitation. So all this turbulence, because we are not running at high resolution, we run at this coarse resolution. For example, for the turbulence, we use what is called turbulence eddies. We use this mixing length. The mixing length, it's not in the nature. You will not see a mixing length in the nature, but we just put this into the model like parameter. We think theory, okay, we will use this parameter, but this is meaning we will use certain parameters, tuning parameter, okay, some tuning parameter, and so this is the issue of parameters. So such parameters are then chosen to make the model behavior as performant as possible. Of course, we compare with the observation and we try to have our model as best as possible. That's why you can ask me why we have 30 global climate models or more. Why? Because the equations are the same. What is different is this process. So every model make differently how to make the subgrid process. You see, so for the radiation, every model have their subgrid process. For the convection, that's why you have different schools. You have one school doing this type of parameterization, another school, and both are correct, but they are different. So that's why we have different global climate models. This is the reason. Next, please. Okay, so then we do this sensitivity to answer to your question. If we put more CO2, how much? So for instance, in greenhouse gas, so we make a model run sufficiently long to reach an equilibrium state. So we run, once we are happy of the model, we run the model for a long time until it reaches the equilibrium, and then we check, okay, the temperature is 4 degrees. The temperature now of CO2 is 4 degrees or other. And then, yes, this is what, we double the concentration, we put double, and then we make sensitivity, secondary, and then we make a sensitivity, and take the difference in global surface, and we compute for the Earth. Next slide. Yes, that's why. So we have more. It's not 30, more than 30 for the IPCC 6 assessment. I think we have 50 or 50 global, but all these models are they have different dynamical core. And also, the most important, different physics parameterization. Every model has its own physics parameterization. That's why we have different models. Okay, next slide, please. Okay, so I told you about the model. Now, maybe very fast about the observation. So, how to observe the climate? Okay, the next slide, please. What we use to observe the model, to observe the climate, is we use what we call weather station. So the weather station is this type. This is a picture in our station. So it's this type of station where we have like we can observe temperature, wind, relative humidity, and you have a good coverage globally of this type of So this is the type of observation. So generally it is between 1.2 and 2 meters above the ground that we put. And what is important is that the distance should be 3 times the height of the obstacle. So this type of observation should be far from obstacle. This is why we don't have observation in cities. Because we are not allowed by the WMO, World Meteorological Organization standard, we are not allowed to put this in cities. But now, the problem, this is what has been shown also this morning, is that we need observation in cities if you would like to see the impact on cities. So this is the next slide, please. And the problem is that, and this is really for climate very, very important, is that, okay, you have a station, okay, but then the environment surrounding the station is maybe changing. Okay, so if the surrounding is changing, for example, this will affect the observation you are doing. For example, if you have your station in a rural area and then this area has been urbanized with time, this is what happened to our station, is that the station was in a rural area and then with time, Brussels grow, and then the city, this station is within the city. So it is now observing also the urban heat island. It's not observing only the, so you have some, what we call the environment change. This is what, so to detect temperature trend, one has to measure humidity as well. Because in the moisture, and then you compute this, because you see, the way the humidity is changing affecting the temperature. So if you have more urban, it means you have less vegetation, okay? If you have less vegetation, means you have less moisture. You don't have moisture, it's more urban. So if you have less moisture, the temperature will change. This is what is here. So we need to know we call this metadata. So if you have the observation, the data of the observation, but you have the metadata of the station. You need to know how the environment change of each station. If you need to take into account. Next slide, please. And this is what we call homogenization. So we need to homogenize the time series. Because for climate, we need long time series, okay? Long time series. But long time series means the station has been relocated. Maybe the station, the instrument has been changed. A lot of things has been changed for the instrumentation, for example. So you need to homogenize this is reallocation of instrument, change of the instrument, change of the surrounding of the shelter. So all this should be taken into account if you would like to use observation for climate. It's not easy. The model is not easy, but also the observation is not easy. Next slide, please. We use also this type of measurement for precipitation. Okay, I show you temperature, but this is also for precipitation. Next slide, please. Wind speed, we use also this type. I see in Professor Surab here will also make some measurement of wind speed here in the campus. Very good. There is a standard is that it should be at 10 meter from WMO, but it should be also 10 times far from the obstacle, because the wind is very sensitive to the obstacle. Wind is very, very sensitive. If you put obstacle, the wind will be reduced very well so you will not measure a 10-meter wind as it's in a rural area. It's really very so that's why WMO we cannot put this in cities. It's impossible because it's not standard to put this in cities. But now, if you would like to study the city, you need to put this into city to study what is the impact, because the wind will be reduced in city because of the obstacle. So you have much more less wind in the city than in the surrounding because of the obstacle. Next slide, please. We use also this, what we call radio sound. Okay, so this is balloon we put into the atmosphere, and then it gives you the profile of the atmosphere. Okay, it's not the same time. It will be because it's going with time. It changes, but it gives you the profile of the. We use this also to evaluate the vertical profile of the atmosphere if it's correct. Yes. We can use also radar. So this is Belgium here. We can also radar observation. I'm sure you have also radar here observation. But this is used. We don't use this for climate because. The radar is not a good estimate of it just gives you the pattern of observation. This is really good. So it gives you where are the observations. But the quantity of precipitation is not very well by the radar. That's why now you see people combine with rain gauge. So you combine radar with rain gauge, you can have some good estimate of the precipitation. But radar only is not, the pattern is good. The pattern can be used. Next slide, please. And finally, we use also satellite. So this is a Severi. So we put this instrument on the satellite, we launch this, and then this will give you some observation. If you go to the next slide, please. Yes, this gives you the S0. You remember S0, the radiation? I told you in the 1000. But it is 11 years. So this is how the solar irradiance, this is constant normally, but it changed a bit. You see here how it changed. We have a cycle of 11 years, how the solar radiation changed, cycle of 11 years, and this is by this, it's satellite, give you this picture. And it can also give you, for example here, this is I think infrared radiation, so you can also estimate this from satellite. The problem of satellite is that you can, for the moment is okay, but before, it's not a long time series, so you need long observation, and there is also problem of homogenization in satellite. So all this, you should take this into account for if you would like to study this. Next slide, please. Yes, and this is the, we can also observe CO2. Huh? This is the atmospheric CO2 at Mauna Loa Observatory. I don't know if you know where it is, this. It's in the middle of, I think, the Atlantic? Or? In Pacific, yes, thank you. So it's, normally it's there because it's really far from, from anthropogenic. This is really good to measure the CO2. And this is how the CO2 is increasing, and I only there is a recent. I just put this because but there is a recent observation. The only way to explain this CO2 is anthropogenic. We did not find, for the moment, any other reason why this CO2 is increasing, except the fact that is from the anthropogenic emission. Next slide, please. Okay, so the observation, and yes, we also use the reanalysis. What is the reanalysis? This is really very well used. So you can have GFS that Subimal showed this morning from America. You can have ECMWF, it's ERA 5 now. Some people using ERA 5 or ERA interim. This is from European Center. What is this? This is a combination of observation and model. So they combine both observation and model, and they give you for example, the latest one, ERA 5, is from 1950, I think, until now. You have really a good estimate of the atmosphere. Now it's every hour. So every hour you have the vertical and then you have the surface. You have really every hour. So you can use this to make downscaling. People are using this to make downscaling over India or over other regions. You can use it to force hydrological model. You can use it to force different, you can use this. It's really the best. It's not observation. It's a mix between observation and model, but it gives you the best estimate of the state of the atmosphere. So a lot of people, we are using this to evaluate the climate model. So when we run climate models, we compare with ERA, with reanalysis, to see if the model has a bias. Because every model can have a bias, warm in temperature or dry bias in precipitation, etc. Next slide, please. Yes, just to finish, this is how the model has changed. This is from the IPCC. So this is in the 1990. So this is the first assessment, and this is the latest one, 2021. So check now, let's start by the model. So these are the climate model. So in the 1990, IPCC used only global model, but now we are using global, but also regional model. What is regional model? The same like global, but for only one region. So you run it over India only. You run it, but then you need the lateral boundary condition, but this is another story. I can explain you later. So here what we call Earth system model, and here it's high resolution model. You see here it's 100 kilometer, but the regional is 25 to 50. So we are increasing the resolution. So these are the process that was, you see we have circulation, ocean, radiative process, land physics, sea ice. You see here we have more, atmospheric chemistry, for example, land use and cover change, land and ocean geochemistry, aerosols and cloud interaction. So we have more process. So the more process you add, the more accurate you are closing to the reality. Now, for the observation, you can see, for example, how many observations? 1887 stations in this period. Look now how much? We have 40,000, you see? So you see the difference of the number of precipitation, number of stations that we use to, there is other change, but this is just to give you what is the evolution of IPCC model and observation. Next slide, please. And thank you. So this is for the first lecture. So maybe you can take a break. Huh? Okay.
So anyone has any questions, we can take one or two questions.
It's clear.
So is there any advancement in the resolution or kind of?
Yes. Yes. Now, so as I said, if you can go to the previous slide with the two models, with the two IPCC. Yes, this one. The last one. Yeah, this one. Yes, so here. So the most advanced that we are trying to do is to do this biogeochemistry, because for the moment, for example, the surface, we don't consider the carbon. So the vegetation is static. So if we have forest, in the model it will stay forest for the 100 years. But this is not correct. We know this. If the climate change, the vegetation might change also. So we call this dynamical vegetation. So this is what we are trying also to do. So there is some models which already do this in the 6th assessment, but we will do also this in the 7th assessment. More model will use the carbon and put it into the vegetation, that the vegetation can interact dynamically. So we can have dynamical vegetation also. So the carbon will be computed also because for the moment we don't compute the carbon from, yes. So this feedback we will do. Another is we go to high resolution. So now the global, even the global start to put urban parameterization in the global climate model. Because even if it's at 100 kilometers, so maybe the next, yes, we will go higher and higher resolution. So they are putting urban also, urban climate. We have also these regional climate models. Now we are running at 50, 25. Over Europe, we are running also at 12 kilometers, but the next advance is to go to, we call this convection permitting, it's about 2.5 kilometers. Yes, 2.5 resolution. So 2 kilometer resolution. And this is really another, because then you have all the process that I show should be parameterized differently. Because one school said, okay, we don't need parameterization. Another school of physicists said, no, we still need parameterization. So there is different school, but this is the resolution on which we are working now. We need to run at this resolution now. So the regional climate, not the global, the regional, because the regional are at 12, but now we are trying to go to this resolution for the, yes, because we assume that with this 2 kilometer resolution, we can catch the extreme precipitation better. So all this flooding and
if we summarize, or if we get the cumulative aspect of the cities which are there,
yes,
within the city, if we have different experiences of temperatures,
yes,
due to the vegetation or due to some other kind of densities.
yes.
So, but in all, if we consider it on a larger scale,
Yes.
then if we average it or something like on a particular scale, then it might affect the climate.
Yes. So
not to the city level, but if you consider
globally. Yes, there is some papers where they just put the anthropogenic heat from cities, and they found that it impacts even the monsoon here over India. The fact that you have, I saw some papers, yes. So the urbanization, it has been said by this morning. So if you put anthropogenic heat, even the global, you can see the impact. But still, only some papers. It's not a lot of papers that found this, but some people found this aspect. Yes.
Thank you, sir.
Welcome.
So we will now break for a tea, and then we'll continue with another lecture
Yes.
with Professor Hamdi.
Yes. This one. Is okay with the online? It's okay. Yeah, it's okay. They can ask questions online. Okay? Yes. Okay. So let's start again. So this, you see here, I was talking about this cooling here. So this cooling is mainly from the aerosols. You remember the first lecture? I told you if you have aerosols, you have a cooling, you see? So that's why it's mainly from the sulfur dioxide. So it's an aerosol. It makes a cooling of the, this is why we have this cooling here. But if you make the total, so you will have at 1.1. So if someone asks you, what is the warming? We are at 1.1. Okay? You remember, a lot of people, a lot of countries say, we will try to limit, it's the Paris Agreement. You know the Paris Agreement? Paris Agreement, a lot of countries say, okay, we will try to limit the warming between 1.5 and 2. So they make this in Paris. They call it the Paris Agreement. But you will see that, just to tell you that this year is the first year where we are sure we will, for the first time, have 1.5 degree warming. So it's from Copernicus, it's a European project. And we compute all the, and this year, it's really unique, the first year where we reach 1.5. In fact, 1.5, it's in the Paris Agreement, we say, okay, we will reach 1.5, but at a mean. But this year is the first year where we will, so that's why it will be very difficult to limit the warming to 1.5, or because already this year is the first year where we'll have 1.5. So just remember, we are at 1.1 degree warming. So this is what I said. So the recent change in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. I show you the picture. And the global warming over the past 10 years, yes, was about 1.1 if we compare to this period. So what is also a key message for this report is that unless there are immediate, rapid, and large-scale reduction in greenhouse gas emission, limiting warming to 1.5 will be beyond reach. And I told you, this year, it will be the first year, global mean 1.5. I think it will be in the news, but maybe in January or... well, so... yes, so the CO2 concentration, as I put here, in 2019 were higher than at any time in the last 2 million years, and concentration of methane and nitrous oxide were at their highest in at least 800. You see that we are really breaking a record for this. So also one thing for this report is that it's for the extremes events. It is indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and drought more frequent and severe. So it's really clear. So in this report, some new mathematical method has been used we call this detection and attribution. So there is an event you detect, and then you attribute the event. Is it due to climate change, or is it due to natural, I told you, variability? So what is the percentage of climate change in this? And in this report, we found that climate change is really impacting the extreme event, and it is really very clear that climate change is making these extremes more frequent and severe. So including heat wave, and you will see in the next slide. So this is also very, we need to make this into our mind, is that climate change is already affecting every region on Earth in multiple areas. So there is no region which says, okay, I am safe from climate change. So there is no region in the world. So every region is affected by climate change. And the change we experience will increase with further warming. So every 0.5 degree warming will intensify all this change that I just said. This is about the extreme precipitation. So since 1950, heavy rainfall events have become more frequent and intense over most land area where there is sufficient data, of course. And human-induced climate change is also contributing to this increase in drought in some regions. But we will see this in the map very clear. Yes, this is very important also. Okay, we said, okay, we would like to limit the warming, but there is some parameter which will never go back. Even if we limit the warming, this parameter will still see change. And these are all related to the ocean, for example, ice sheet, sea level. So these parameters, because they are slow parameters, even if we stop the emission now, these will still keep going, keep going for thousands of years. Because this we call the slow response system. In the climate system, you have a slow response and you have quicker, but this is the slow response. So they will not be, they will still be, so they will not be stopped by limiting the warming. But we can have reduced the warming in some. Yeah, this is also very nice. So it will give you an order of magnitude. So suppose that we are here, okay? And you know the IPCC use scenario in the future, some projection, okay? So we have either we say, okay, we keep, this is the high emission. So it means that we will not do a lot of mitigation. We will just emit as we are doing now, okay? So we call this the high emission. There is another one, highest, but this is high. And then we have the low emission. Here you see that we will succeed to reduce the emission. This morning we heard about net zero. So India is committed to have the net zero, I think, around 2070 or 60. 70, I think. 70, yes, 70. China is 2060, I think. And then in Europe, they are focusing on 2050, I think, 22 net zero. So okay, so these are the two scenarios that we will take, and this is the emission, okay, from the ground, emission. So now we are here. So how many years we need to see if we follow this, if we reduce the emission following this scenario, how many years we need to wait until we see the impact on the concentration in the air? Okay, so we have the emission from the ground, from industry. So how many years, we say, okay, we will reduce. How many years we need to wait until we see the impact on the concentration, on the air? This is here, so you need between 5 to 10 years. So if you reduce now, you need between 5 to 10 years to see the impact on the air. Okay, so it takes time. Now, how many years you need to see the impact on the surface temperature? I told you, we are at 1.1. So how many years we need to see the impact? You see, we are here. So we need between 20 to 30 years reduction. So that's why I told you this Paris Agreement limiting between 1.5 and 2 is really beyond reach. Because even if you stop now, you need between 20 to 30 years to see the impact for the temperature. This is only for the temperature, but for the sea level rise, it will still keep growing, increasing, because it's a slow process in the climate system. Okay. So, to limit global warming, strong, rapid, and sustained reduction in CO2, methane, and other greenhouse gas are necessary. This would not only reduce the consequence of climate change, but also improve air quality. I will talk about this. So, while CO2 is the dominant greenhouse gas and reaching net zero CO2 is required to limit global warming, strong reduction in other greenhouse gas emissions are needed. And I told you about the methane. The methane is also now very focused. In Europe, we are also focusing on reducing methane because in 10 years you see the effect. It's not like CO2. This, I think, no, it has not been shown this morning. But this is the same like what Subimal showed this morning, but this is about hot extremes. So these are the observed, so what is this? Yes, the observed change in hot extremes. So we take the hot extremes in the world. So this is Europe. We are here, India. So this is the South Asia. So India is part of here. And you can recognize this is America, South America. This is Africa. Okay. So we are here, and this is the change. It's observation. Observation. So if it is red, means an increase. So we have an increase in hot extremes. So we have an increase in hot extremes in India here. And what does mean this tree? This means that we are high confidence that is due to human contribution. So human contribution is, we are highly confident that this increase in hot extremes in India, for example, here, is due to human influence. So this, you showed this morning, Subimal showed this. This is for precipitation, the same here. So we have an increase of heavy precipitation, but as Subimal explained this morning, this is due to limited agreement. So what does mean limited agreement? He explained this very well this morning, but it's just that you have some local effect, maybe some which drive the trend in another direction. You have global effect so you have some difference, and you don't have this, all the papers don't converge to the same conclusion. So you have limited. We say this limited agreement. So we don't have an agreement on the type of change because of monsoon, because of large-scale phenomena, local-scale phenomena, urbanization also enter here. So that's why we have limited agreement on the type of change. We have the same. If you see Europe here, Western Europe, we have the same aspect because we have also some large-scale phenomena and local-scale going also. Yeah. So we don't have we have limited agreement. So yes, I told you about the scenario, future emission. So future emission will cause additional warming with total warming dominated by past and future CO2 because it's not only future CO2, it's also the past. So all the emission, historical emission, and this is mainly by US and Europe that contribute a lot to this. You have the historical emission, which is also very important to take into account. So here you have all the, we call this SSP, so socio-economic, I think, scenario also here. And you have this 8.5, 7, 4.5, 2, and 1. This means it's in terms of radiative forcing. We call this the radiative forcing, how much in watt per meter square of radiative forcing for it. So this is really the highest one, is business as usual. You see, we are here and we go to 2100. So we don't do anything, you see. So we will follow this path. And I can tell you that until now, we are really following this path. So if we, yes?
Sir, this year, 2024 and even 2023 have seen a lot of extreme events in Europe, particularly in Europe, like drying of Rhine River, and Danube River was also a little bit dry.
Yes.
It was very difficult to navigate there.
Yes.
So, do you think it was due to anthropogenic reasons or due to lack of agreement? Those things are coming.
Yes, so we make this. So first, I will answer in two ways. So the first one is that, for example, in Belgium, we had also in 2021 heavy summer precipitation. We have a flooding in Wallonia, so we have a lot of even death. I think 10 people dead, and we have a lot of cars, etc. So it's a flooding. So we made an attribution study. So it's a statistical study. We wanted to know how much of climate change contribute to this event. We found that it was not that much. We found only 18% due to climate change. So it's not purely due to climate change, this extreme. I don't know about the new one, for example, for Spain. There is a new one, flooding in Spain last 2 months. They are now making the study to see how much of climate change is affecting, is contributing to this extreme event. So it's still undergoing. So I don't know how much. The other thing is that we found that over Europe, the internal variability is still impacting a lot until 2050. So the extreme event will still be impacted also by the internal variability still. So we cannot see that it's really due to climate change, the extremes that, but I think I have some slide of this, yes. Thank you. So voila, so these are the scenario, the business as usual, and this one is a really optimistic one, but I think, yeah, it's really very optimistic. So as I said, we are for the moment following this path. So if you put the observation here, we are really following this path. Okay, so now, I told you in the first lecture, we built the global climate model, we put all the process, and then was the question, we run for 100 years, and we see what is the new radiative equilibrium of the Earth. So if you run with this scenario, you will see that the new radiative equilibrium, it will be 1 here, maybe 1.5. This one, you go to this level, SSP2 here, 3, and okay, the SSP5 is the most, you see, we are more than 4.5 maybe warming. So depending on you have different sensitivity. This is what I show you in the first lecture. Okay, so now let's see how it impacts, see this on a map. So what you can see here is that with every increment of global warming, change gets larger in regional mean temperature, precipitation, and soil moisture. So this is for temperature. So observe a change if we reach 1 global warming. So if we reach, now we are at 1.1, so we already are beyond 1. So this is the simulated, and this is the observed. Okay? And this is if we reach 1.5, if we reach 2 degrees, and if we reach 4 degrees. Yeah, it's This is how it will behave. So India is here, you see, so it will be really a difference between 1.5 and 2 and 4 also. But I have a question for you. So tell me, why here we have in the north, we have higher warming than in the other part? Yes, it's the feedback. I told you about the feedback in the first lecture. We have the feedback with the ice. So all this is the glaciers. You have some, so if you have warming, you have glaciers will melt, you have permafrost, etc. will melt, and this will, yes, and then it's a feedback. It will make your temperature more warm, okay? And then again, more warm, more melting, and okay? So this is happening in this region because of this feedback that I show you. So the feedback is, that's why the feedback is very, very important, okay? So this is for precipitation. So this is the simulated change at 1.5. So we can focus on India here. How the precipitation. So it will be a little bit from 0 to 10 here. So we don't see a big change. The same here for 2-degree warming and here of 4. So we see all this region here having more precipitation at 4. But what is very hot is if you look to the Mediterranean basin here, that's really a hot area. So this will experience a big problem of drying and hot temperature and less precipitation. You can see here, if you focus, the basin, the Mediterranean basin from the north and the south will really suffer a lot from this, from the impact of climate change. So this is for soil moisture, yes, the soil, so everything related to agriculture is very important to know, because if you have soil moisture less, you need irrigation, you need to irrigate, and some land, you don't have easily the water. So it's really very important to know. So again, the Mediterranean basin, you see, it will suffer a lot here. India, here we still have like a wetting, so it will have a wetting of the soil. So with respect to agriculture here, you see that we have a wetting. But if you look to other area, Mediterranean, South Africa also here, you see that it will suffer also from a drought. So now let's talk about the extremes, okay? So the projected change in extremes are larger in frequency and intensity with every additional increment of global warming. So I told you that global climate change is making the extreme more frequent and more intense, okay? So let's look here. So if we reach 1.2 degrees, so I told you we are at 1.1, okay? So 1.2, these are the future global warming level here, 1.5, 2, 4, yeah, here 1.5. If we reach 1.5, 2 degrees and 4, and these are the extreme. So the extreme, for example, let's take the 4-degree global warming. If we reach 4 degrees, you will see that the extreme will likely occur 9.5 times here. And it will make the intensity 5.1 hotter. So it means that this is the frequency of heat wave, for example, will be 9 times more frequent and 5 degrees more extreme. So you can see here for the other, this is for the 10-year event. So it's an event with return period. You know about the return period, right? So how the extreme, we compute the return period of the extreme, and here we compute for 10 years. So, and here for 50 years, return period. You see here that the extreme of the extreme, let's say, so it's really the very extreme will be 39 times more. So the extreme of the extreme will more frequently, will happen more frequently. So here the same for precipitation, the same here. So how the frequency and also the intensity of the extreme precipitation over land, and this is also for the drying region. So this you can read. I will not. Very important things that I told you in this report is that we use global climate model, but we use also regional climate models. I will tell you, and this is really new for this assessment report, 6th assessment report, is that the IPCC make an interactive atlas. So you can go to this page, web page, I can send you and then you can select, so it's all over the earth here. You can either compute a map over all, or you can just select here, for example, over India. you can select this region, and then you can see the temperature precipitation only over this region, only over India. But this is, for example, the mean temperature change at 2 degree warming. So if we reach 2 degree warming, what will be the temperature change here? This is the website I told you here, Interactive Atlas. So you can go to this website, and then you can select, you can see the temperature, the precipitation, how it will change for India, for example, or for your regions. Because this is the new in this report, is that we have also regional information, so high resolution. Okay. So let's have a focus on India here. So I go to this interactive atlas, and then I select only this region to show you what will happen here over India. So here, what I put here is this is the annual mean temperature. So the temperature mean, annual mean, and this is at warming of 1.5, 2 degree, and 4 degree warming. You see how the temperature will change. This is the total precipitation during winter, DGF, December, January, February. So this is the total precipitation and how it will change. This is the precipitation summer precipitation for different warming. And this is very important, is the maximum number of days, where you have the temperature maximum during the day over than 35. So if you have over than 35 degree, you will see that for India, very clear, that it will impact a lot here India, the temperature, the maximum temperature in the future. So it will really, here you can see it's even over India. If we look to the precipitation here, for example, you can see for the winter, so there will be a little bit of decrease here, of a little bit, but maybe it's not significant. But here it's significant. All this is significant. And then a little bit of increase here if we reach 4 degree warming. But for the temperature is overall warming here, you see. But if you, for 4 degree warming, you see that the north is warmer than the south here. But this is due to this feedback that I told you. Okay. So here, everything related to human is really very important. So urban, because you need to add to this the fact that you have cities. So if you are in the cities, but this we will see tomorrow, the lecture on urban heat island, because in city, so this degree here, so you need to add on a mean 2 to 3 degree of urban heat island. And urban heat island is not CO2, is not greenhouse gas. This is not related to greenhouse gas. Urban heat island is related to city. It's how do you build, we will see tomorrow this. So you need to add, and how this interacts, how climate change interacts with urban heat island. So this interaction, maybe it will increase or decrease. So this we will see tomorrow. So you need to take this into account.
So for India, if you see for the change in temperature,
yes, here.
It's not that drastic as the northern portion. It is rather smooth, and for number of days over 35, we already have very harsh summers.
Yes.
So is that really a change? Yes, that is a change. Maybe the number of days are going to extend. We are getting wetter in the summers, and that might cause urban floods. But temperature-wise, we are still at a better position, and why is that?
So why here we have the more
for the first case.
Here the temperature.
Compared to the north.
Yes, I can, yes. So this is the
temperature is not that drastic.
Yes.
Number of days over 35 is increasing.
It's increasing.
We already have those.
Yes.
The only thing that I see is the precipitation is changing drastically.
Yes.
When compared to the rest of the world.
Yes.
So why is the temperature not increasing that much?
Here.
But the precipitation is increasing.
Yes, because here you have this, you can have also interaction to a large scale. You have the monsoon also, which impact this. I am not expert on the India climate, but I can imagine that you have different interaction. You have the monsoon effect. But for your question, why here it's not clear and why here it's clear, because the change, this is the change on the mean, and we know that to change on the mean is different from the change in the extreme. This is the change of the extreme. The change of the extreme, because this is, we can call it extreme, is the number of days over a threshold. So this is much more higher than the change on the mean. So that's clear that, for example, even in the last period, we saw that, for example, in my country, in Belgium, we computed the change of temperature in the max and the change of the the summer. Yes, the change. So the Tmax. So the maximum temperature during the day. Okay, we compute how this changed, and then we compute how the maximum of this changed, like heat wave, and we found that the maximum, so the heat wave, the intensity changed much more, increased much more than the mean. So climate change is impacting the mean less than impacting the extreme. So that's why here we see the impact much more clear on the maximum temperature. Yes. Yes.
Then why do we see drastic change in precipitation or wetness?
Here?
Yes. We do not see that much change in the temperature, but a drastic, even for the world map.
Yes.
On the top.
Yes, because the change, the temperature is a smooth parameter, while the precipitation is very local. So that's why you see here, for example, you can see you don't see. You see some difference here, even for India here, some difference for but here you don't see it because the precipitation can be very local, the impact, while the temperature is more like homogeneous. Of course, if you go to deeper details, you will see the difference of city, lakes, but this is done by, I think, global climate model. This is global climate, so 100 kilometer resolution. So you see, but I am not expert on India climate, so. Yeah, please.
Actually, monsoon is a global. It is affected by the global phenomena. It is related to Pacific oceans and southern temperatures and moisture availability.
Yes.
While the temperature is the local, means the amount of insolation is based on India's. The amount of insolation is coming from sun, so it is dedicated to India only. But for monsoon, the phenomena is being affected by the situation in Pacific, situation in South Indian Ocean. So that's why changes are different.
You have large-scale circulation, yes, which impact, yes.
So equalizer effect of the oceans has the effect on the temperature, because wherever the ocean will be there, due to ocean current, temperature will be all over, normal temperature will be there. You can see the coastal area, most of the land masses, it is almost
here.
In the temperature.
For temperature, yes.
It is almost similar in all the coastal.
Yes.
Which are facing to the ocean.
Because it's impacting a lot the coastal, what happening in the coast, yes.
But Gulf does not have the same effect. It has a harsher effect. Gulf. It is on the same latitude, but it has a harsher effect.
It is in the Gulf region.
Yes, the Gulf region. It is in the same latitude, but it has a harsher effect. India and that
Here.
part of Japan has a better effect according to the situation.
It is already desert area. No, that is already desert area. Those of African part.
And just to tell you that this is a mean over 30 global climate model. So it's not only one model, it's a mean. So, yeah. Okay? So now let's see the change in the Asian monsoon. So what we found is that the South and Southeast Asian monsoon has weakened in the second half of the 20th century. This is with high confidence. And the dominant cause of this decrease of the South and Southeast Asian monsoon precipitation since mid-20th century is anthropogenic aerosol forcing. So due to this aerosol forcing, you see that we found, it was observed that the monsoon has weakened. You see again the aerosols, how it can impact the climate system. So the dry north and wet south pattern of East Asian summer monsoon precipitation change result from the combined effect of greenhouse gas and aerosols. So this is with high confidence. And in the near term, South and Southeast Asian monsoon and East Asian summer monsoon precipitation change will be dominated by the effect of internal variability. So this is with medium confidence. You see again that in the near term, yeah, the effect, this is what we saw also for Europe, that the internal variability will still be the dominant factor. So the climate change will not be seen until more beyond 2050 that we will see the impact. So until 2050, still the internal variability will impact a lot the precipitation, and also here the monsoon. Huh? So in the long term, South and Southeast Asian monsoon and some Asian summer monsoon precipitation will increase. But this is with the medium confidence. We found also that the urbanization, I told you this, urbanization in India has impacted. So I found some papers where they found urbanization has impacted the monsoon precipitation also. But it was with medium confidence, because I did not find a lot of papers that converge to the same, so limited agreement. So this is the region that, I show you here. So South Asia here, heat wave and humid heat stress will be more intense and frequent during the 21st century, medium confidence. So heat wave, this I told you, over the region here. Both annual and summer monsoon precipitation will increase during the 21st century with enhanced inter-annual variability. So, but let's keep in mind that this is really will be an important issue here, this heat wave and humid heat stress, because you combine temperature and humidity. I selected here this is from working group 2. Working group 2, this, I just select this because there has been some city here in India. So what is this? This is a key risk and adaptation option in selected cities across Asia. So let's focus on South Asia here, Ahmedabad and Mumbai here. You see that for urban heat island, for example, the key risk, urban heat and urban heat island is, what is this? This is the risk level, large, okay, and the risk evidence. If it's this color, it's high. So it's high risk level of urban heat in Ahmedabad. Mumbai, I don't know why they put here, I don't know. Maybe less research paper or, But here it's really very clear. You see that Ahmedabad will be important risk. Let's see, they also make the progress. What is the progress? Is the progress level, is it high, medium, low, and the progress evidence? So how the institutions are taking this into account? Institutional, infrastructure, ecosystem-based, and behavioral, also people. You see that if we look to the Ahmedabad also, here you see that the progress is quite high. So there is a quite high progress in this city concerning the urban heat island. So they are taking some measures and they are taking this into account. Voilà, so this is, I just select this from the working group 2. So just to finish, just to tell you, what is this? So this is the cumulative CO2 in gigaton, okay? And this is the warming. So how much of, if you put more CO2, how much of warming you will get? So this is the historical global warming. I told you we are at 1.1, we are here, okay? 1.1, and this is the relationships between CO2. It's more or less linear. You can say it's more or less linear relationship. So the more you add CO2, the more you will get temperature. So now let's count how much, so with current emission, how much we emit per year, global, we emit 40 gigaton globally. The Earth emits 40 gigaton per year, and accounting for land and ocean carbon sink, because there is also sink from land and carbon. You know, forest sink. There is a carbon sink for forest, for example, and the ocean is also absorbing the. So taking this into account, we are emitting 40 gigaton. So this amount would be reached in a matter of decade, because per year. So per year. So 40 per year. So let's see. What is here? Each gigaton accumulated in atmosphere cause. So this is each 1,000 gigaton accumulated cause this increase. And so if we, just to tell you that with this warming, I think it's here. Yes, it's here, yes. So we are emitting 40 gigaton per year, okay? 40 gigaton. So this is the historical budget that has been, okay? So the remaining budget, how much of budget we still can emit if we would like to limit to 1.5 and 2, okay? So if we would like to limit to 1.5, we need to, this is the budget that we have. We need to emit less than 400 gigaton. So 400 gigaton, every year we emit 40, so it means 10 years. In 10 years, we finish this budget for 1.5. So now if we limit to 2 degrees, so it's 1,150. So you see that it's a matter of decade to reach this carbon. So just to tell you, we are at 1.1 degree warming. This year is the first year where we observe 1.5 globally. And if we would like to limit to 1.5, the 1.5 is mean on an average of 20 years. Or we need to limit to 400 gigaton. So it's a matter of decade to reach this. Voilà, that's it. Thank you very much. So just to say that tomorrow we will focus, make a zoom on urban area. So this is just to give you a large-scale view. First, what is global model? Second, what is the state of the climate? And tomorrow we will focus on cities. And we will see the interaction with the urban heat island.
So any doubts or questions? In between, might have asked.
Yeah, and I am sorry if I could not answer to all your questions because, as I said in the beginning, I am not expert on all. So I am just adding a little bit on the interaction. So why I was selected, it was for the urban climate. So I contributed this report in the chapter 10. I contributed to the observation and I contributed to the urban heat island and interaction with climate change. So how to provide urban heat island phenomena. So it's really, you cannot be expert on all this, it's impossible. So but yeah.
Sir, you would like to say anything?
Yes, the questions, those
Yeah,
are I
questions.
would like to answer if you open.
Sir, good answer.
One question which was asked in terms of averages. No, no, no. And you can go offline.
No, sir.
No, you can go offline. No, I would not like to be
Did not do.
Subhadra, go offline. This lecture is over. Let's stop that.
It's offline. 2 points were raised in discussion. One which he had raised, that when we are seeing the temperatures and when we are seeing the rainfall, why there are differences. Yeah. In rain, when you are seeing, you have to observe 2 seasons. One, the winter rainfall, when in India the rainfall would decrease. So winter crops would be affected because we would have less rainfall in winter. In summer, the rainfall would increase and intensity of the rainfall would also increase. So 2 things we need to observe over there. That number of days with rain may reduce, but the total rainfall would increase. So there will be, whenever it would be rain, it would be heavy downpour. So you have extreme rainfall events increasing. You would have more rain during summer. You would have less rain during winter. The cause is very, very simple. If the temperature is increasing, during winter you would not have sufficient effect of rain-bearing clouds coming to India, which primarily come from the coastal area. As the temperature has increased, that force would reduce. During summers, when the temperature
smart cities.
Good evening everyone. My name is Manish Ravat. I am currently pursuing Master's Urban Planning second year student.
Good evening everyone. I am Saranshna Mathur, research associate in SCSR Project Management.
Good evening. I am Architect Sari Jain. I completed my bachelor's and my master's, and currently I am a PhD student at Planet, and my research topic is related to real estate and finances.
Good evening, myself Anshuman Sahu, and I am currently pursuing Master in Planning in Urban Planning from IIT itself.
Good evening everyone, I am Harshita and I am pursuing my Masters of Technology from IIT Bhopal in Geoinformatics.
Good evening everyone, my name is Neeraj Jatap. My PhD is in IIT Bhopal. My research area is GPS study on hydraulic structure.
Good evening everyone, I am Rakesh Mistry. Right now I am doing PhD under Dr. Surme and my topic is climate law.
Also, everyone, I am Shubham Mitra. I am also pursuing my PhD in the Department of Architecture and Planning in Manet. And we have a lot of fellow participants also who has joined us through online mode. With this, we'll wrap up today's session. But before going, we should know tomorrow's schedule. Tomorrow at 9:30, we'll again reconvene the session. At the first lecture that we have is Dr. Divya Sharma. Second will be again Professor Hamdi. And then we'll have our local expert, Dr. Survi Malhotra, who will take the next sessions. Thank you so much.